ఇప్పుడు ఏదైనా చేసుకోవచ్చు కదా నేను. ఇక్కడ రావాలి, మళ్ళీ ఇక్కడికి వచ్చేస్తాయి. Very good afternoon. Are you able to hear, all of you?
Good afternoon, sir.
Good afternoon, sir.
Audible. Okay, fine. Are you able to see the screen?
Yes,
Yes,
sir.
sir.
Training testing and is visible. Huh? Okay.
Yes, sir.
Okay. Thank you. Today is the last day. Today is the last day of our workshop.
Yes, sir.
Just I will give a brief introduction to the LSTM. Then after 3, Venkatamana will take over. And before that, I want to talk about in the last class when I was delivering some lectures, someone was asked training, testing, what is validation and all that. Just briefly I will talk. Then I will switch over to the LSTM, recurrent neural networks. In this one, as you will know, when we are doing the train the neural network, as most of the time, what I will say is that if you know how to generate the data, okay, then your 50% of the job is over. Therefore, when data is generated, okay, therefore, as you will know, what we are discussing is approximately 70% of the data will be kept aside for the training, another 30% for the testing. Therefore, once again, under that 30%, what we will do, 15% for the validation and 15% for the testing and all that. Therefore, with respect to this one, what is validation? Validation is evaluating how well system is learning. Then, how do you validate a system? By showing it new data, okay, it has not been before, that is the new data set. That is why what we will do is that most of the time, as I'm mentioning, the testing data or validation data should not be part of the training data. Suppose the data, whatever you are testing or validating, it is a part of the training data, then there is no question of whether it is my network is working well or not, I cannot test. Therefore, most of the time, it is like whatever I will teach in the class, okay, some derivation is there. Same thing I done, same thing I given to in the class also, in the examination also. Students will do very easily. Similarly here, the validation data and testing data should be different. That's why we are keeping aside that 30% of the data. Therefore, by showing it to the new data, it has not been seen before and measuring how accurately it works. And we want to check based upon the new data, what is the accuracy. Then what happens after validation? If predictions on validating the data are good, if you want to predict something, okay, I want to calculate something, I want to get the output something, okay. If predictions on validating the data are good, deploy system. That means when you are 15% data we have kept aside for the validation, when you have given the new data and my results are fine, then it is okay. Otherwise, what we will do is that if not good, okay, error, if not good means error is more, then go back and train some more, okay, add some data and train some more iteration like that, or otherwise we can change some parameters, etc., etc. And one more thing, apart from the validation, there is some cross validation is also there. Generally, the cross validation, this is separate, specially useful for data. When data set is very small, we will use some cross validation, but most of the time, people will use for the validation only. Okay. Okay, let's train and test a categorizer. That is, for example, for the classification problems. Here, we will illustrate the idea in this module using a supervised categorizer which we will teach the label data. That is, as you have seen, yeah, I want to train the network, that is supervised learning, okay, and some features are there and labeling is given, okay, just like I want to give, for example, I want to separate as a classifier LG for some data, some features I will take, it is for the LG fault, some features I will take, LL fault, LLG fault, like that I will label, okay. Therefore, in this one, as you will know that it's present each sample in the training set to classifier one at a time. For each sample, give the sample's features and ask it to predict its category. If prediction is correct, then move to the next sample. If prediction is wrong, feed classifier's output and correct the label back to classifier. Therefore, here in this one, most of the time, as I was mentioning in the beginning of this workshop, that is more data, more accuracy. Less data, less accuracy. Therefore, in this one, when anything is gone wrong, okay, therefore we can, if we enhance the data, okay, or otherwise by modifying the initial weights, okay, or learning rate, sometimes we will get a good results. And how long to train epochs? Epoch, that is epoch or iterations, both are same. Epoch is a run through the entire training set. Usually you must train through many epochs. This is based upon the problem, okay, it will take 1,000 iterations or 2,000 iterations or more than that also sometimes. Keep training as long as the system is still learning and improving its performance on the test data. Therefore, as you will know, as we are discussing, you have to train until error is very, very small, 10 to the power of -3 or 10 to the power of -4. Then only we will stop training. After that, we will go for the testing. Stop when system's performance is good enough for the task. Okay. Stop also if you are out of time. Suppose based upon what are the stopping criteria you have kept, based on that one, we will proceed.
Yeah.
Okay. Yeah. In this one, as we are discussing input data, that is nearly 70% for the training set, another 30% for the testing. We will separate. Once again, what we will do is that is input data. Once again, training set is 70%. The 30%, whatever the data is there, some approximately 15% for the validation set, another 15% for the test set. That is training, validation, and test set. And one more thing with respect to this machine learning, or in this one, we will talk about overfitting and underfitting. Anyone knows what is mean overfitting? What is the underfitting? Okay, what is underfitting? Our model is underfitting when it does not learn well enough from training data. Then it is not learning from the training data. Then how we can overcome this when your training is not proper? That's why less data sets, less data, less accuracy. More data, more accurate. That is my buzzword. Therefore, our model is underfitting when it does not learn well enough from training data. Underfitting describes the situation when our rules are too vague or generic. We can often cure underfitting just by using more training data. Therefore, why it is become underfitting? But data is very, very less. Our data sets are very less. Then by increasing the data number of data sets, we can overcome this underfitting problem. With more examples, the system can work out better rules for understanding each piece of data. Therefore, underfitting is usually much less of a problem than overfitting. Then what is overfitting? When our system learns from training data too well, training is done very well. That is by training, because we will have two types of errors will be the training error and testing error. At the time of training, my error is 10 to the power of -4 or -5, something like that. Okay. Then I will stop training. Therefore, when our system learns from training data too well and does poorly when presented with the new data, when I want to test with the new data, then errors are more. That we are calling as the overfitting. Therefore, overfitting results from using rules that are too precise. That is here, if you see a curve fit to the tempo data, that is curve fits too well, it is overfitting. That is testing is erroneous one. Then how we can overcome this problem? How we can overcome the overfitting problem? Underfitting by adding more number of data sets. Overfitting
by reducing model complexity, sir.
How we can reduce the model complexity? Model, what is the model here? Model is neural network only, is it not? Yes or no?
Yes, sir.
Then how we can reduce the complexity? Suppose, as you will know, suppose I'm using back propagation algorithm, then input and output layer nodes I cannot. Only you can model, we
Hidden
can
layers.
change with respect to the
hidden layers.
hidden layer. Other than that, anything is there?
Learning rate, sir.
Okay, that is also one of the things, the learning rate, initial weights. Okay, because in the overfitting is coming to picture, as you have seen, everything is fine. Training data, training area is also very, very small, but it is coming with respect to the testing.
Yes, sir.
Okay, this one just I want to talk about a few 5-10 minutes. Then I will switch over to the okay. What is the need to use recurrent neural network? Any use is there because suppose I'm happy with the back propagation algorithm or some other function and all that. Then what is the need to go for this recurrent neural network? Or before going to the recurrent neural network, what are the issues with respect to the feed forward neural network or whatever we are having this conventional neural network? Because we are talking with respect to the in case of recurrent neural network, the data should be, we should give a sequential, because if we want to talk about this recurrent neural network also as known as the sequential networks. Therefore, we will use for the load forecasting or language processing text. Okay, Rama is going to school. It is a sentence. Therefore, after Rama going school is sequentially, is it not? Just like our load forecasting also will give the data t-1, t-2, t-3 dot dot dot. Then I can predict at t+1 what is the my load or etc. and all that. Therefore, in this one, I'm comparing with respect to the conventional back propagation algorithm or feed forward neural network. In that case, it cannot handle sequential data. And second one is that it will consider only the current input. That is, whatever input you have given, suppose the data and training the network, say that input only will consider. It will not bother about what happens, what is the before that data, what is there, after this data, what is there, just like that, what we have seen, t-1, t-2, t-3, like that. Okay, it will not bother in case of the conventional neural network. It will consider only current input. And one more thing is that the conventional neural networks cannot memorize previous inputs, because there is no memory in case of the BPA, like that algorithms. Therefore, if memory is there, then only you can able to remember. Therefore, to overcome this one, the best solution is the recurrent neural network. That is, once again, I'm repeating the limitations of the conventional neural network or shallow neural networks. It is that cannot handle sequential data, that is continuous some load or language, whatever it may be. Consider only current input. It will not bother about previous and after that one, and cannot memorize previous input. Therefore, there is no memory. And one more thing, then what is the need to use this deep learning? The deep learning, we have seen one of the algorithm, conventional neural network. Suppose you take in the case of deep, suppose you take a back propagation algorithm. Generally, what we have considered is that we are an input layer, we are having the hidden layer, and as well as the output layer. In the hidden layer, instead of taking one hidden layer, I will take 1,000 hidden layers. I will take hidden layer 1, hidden layer 2, hidden layer 3, hidden layer 4. Then what is the issue? An issue will be there. Here we are in case of convolution neural network, I'm convolving image as well as the filter. Then after that, ReLU, I want to make it non-linear. Like that, we will have filters will be there to extract feature extraction. Several things are there. We'll have several things. But here, my question is that you are having BPA. Instead of one hidden layer, you take 1,000 hidden layers. Can I call, if I call that as the deep learning or deep neural network, then what are the issues in that case? The most important thing is that there is one limitation is there. Anyone can tell what is the limitation? If we use conventional neural network as a deep neural network. Conventional means always when I use the word, let's say think it over, it is a back propagation algorithm. Okay. Any issue?
Sir, gradient, diminishing of the gradients.
Yeah, vanishing gradient problem. What
Vanishing
you call.
gradient problem. Yes.
Okay. What do you understand by vanishing gradient problem? Because this BPA, it is based upon the steepest descent method. It will have some derivatives. Then
Weights
when you
doesn't
take,
change, sir.
which one?
Weights doesn't change actually.
No.
Weights doesn't
No.
update after vanish.
Oh.
Gradients vanish.
Oh. That is in this one, suppose if you see in the back propagation algorithm, the derivation also sent to you. That is, if you see, a gradient should exist. That is what your rate of change of weights is dou E by dou W. Therefore, in this one, what happens when you are having large number of weights, the gradient should continuously it should come up to after some input layer to the after coming from input layer, that is what we call first hidden layer to the last one, it should go. Therefore, because of it will move when number of hidden layers are more, then gradient may not reach. That is why in case of the back propagation algorithm, our one condition is that we should make use of continuous activation function. Why we should make use of continuous activation function? My derivative should exist. If the derivative is not existing, suppose if you take linear neurons, then back propagation algorithm will fail. Therefore, to overcome this vanishing gradient problem, we will also go for this deep learning, etc. and all. Okay, come back to the recurrent neural network. Most of the time, this recurrent neural network is nothing but people also will call as a feedback neural network. That is, output is fed back to the input and all that. Therefore, the topologies are different and all that. Therefore, we can also call sequential networks. Therefore, if you see this slide, when we work with sequential data, we need to use special care to preserve and make the best use of the order in which the data arrives. Suppose in the language, okay, a sentence as I was mentioning, Rama is going to school. It is a order is there, Rama going to school. Therefore, what you are talking is that when you want to preserve and make the best use of the order is very, very important. In case of electrical engineering, the load forecasting, the data T minus 1, T minus 2, T minus dot, T minus k like that. Okay, so that is sequential. Okay, we will see a variety of special architectures for just that purpose. How to make use of sequential data. Therefore, in this one, if you can see first of all, what do you mean by sequences? So far, we considered every sample as a standalone entity, comma, unrelated to any other samples. What is standalone entity? I was mentioned some of the limitations in the beginning, 3 limitations. That is, consider only current input. It will not bother about what is before that data, what is that, and after this, what data is, it will not bother. Only it is standalone. That is, consider only the present input. With respect to that, it will proceed. Therefore, so far we consider every sample as a standalone entity, unrelated to any other samples. That is, it will have its own. Okay, it will not bother about others. Because there is no sequence. This makes sense for things like photographs. This makes sense for things like photographs. For example, if we are classifying an image and decided that we are looking at a cat, it does not matter if the image before or after this one was a dog or squirrel. Just like with respect to image point of view, what we are talking is that suppose I want to give the input as a cat, that image of the cat, it doesn't matter. Suppose if we're talking about like a conventional neural network, before the cat, It is a dog is there or squirrel is there, doesn't matter, or aeroplane is there. The images are independent for each other. Okay. For example, if an image is a frame of a movie, then it can be helpful to look at it in the context. Context is okay, bold context in the context of the other images that precede and follow it. For example, once again, if you see a video of a ball flying through the air, okay, this is the sentence: video of a ball flying through the air. We can use a CNN to identify the ball's position. We can identify the ball's position, but CNN cannot tell whether the ball is rising or falling. That is a limitation with respect to this CNN, because it is also feed forward. Only thing is that difference is that feature extraction. That requires knowing what come before. That is, we should know what is the before, what is the after. That is what we are talking the sequence. Therefore, in other words, we need some context. If you need some context, then use the recurrent neural network for this lecture, which are context based. Okay. Sequences. What is a sequence? When data is arranged so that each piece has some kind of relationship, these pieces that come before and after, we call that a sequence. Some relation is there, just like a load data point of FFC, T-1, T-2, T-3. T-2 is having some relationship with T-1 as well as the T-3. With respect to language, the sentence also, Rama is going to school, Rama going to school. Some relation is there from one word to another one. Therefore, we call that type of things as a sequence. We will look, in this one we can talk how we can work with these kinds of sequences to derive meaning from them. One more question, give some examples of sequences. That is series of readings of, what are the examples for the sequences? Example, noon time, temperature of a specific place over a period of days, time of high tide each day, price of a stock at the close of trading. And most of the time, if you see in this one, last one I will try to discuss trading, okay, stock market. Similar to our load forecasting, in case of the stock market also, suppose the prices of a Reliance company is there. Today is each time, as you will know, in the stock market, every time to time, the share value of a particular company shares will goes on, may increase or may decrease continuously, or they may stand still also. Therefore, based on today, how the price of a company's share market, okay, some company, either Tata Motors or it can be Reliance Industries, whatever it may be. If I know time, 10 o'clock onwards, I will check T equal to 10, 11 o'clock, okay, something like that. Every time I will note down, every 1 hour. Therefore, based upon not 1 day or one day data, I cannot predict. Based upon, I will take 1 month data. Then based on this one, I can predict tomorrow, okay, or Monday, what is the stock price. Therefore, it requires a sequential data is required. Otherwise, we cannot. Random data and all that, it will not work. This type of things. And some more examples for sequences is that stock prices over a series of days, that is most of the thing, a series of days. Notes that make up a song. When a song is there, a sequence of words should be required. Notes that make up a song. Frames making of a movie, several frames will be there. They should be continuous. After this frame, next frame should come like that, the process. Or words from a language. All are based upon the sequence. Sequence is required. We ask questions about all of these sequences, such as what will be the stock price be tomorrow? What will the stock price of tomorrow? As I was mentioning, I'm having large data is there. 1 month, 2 months data is there. Based upon this one, I can predict. Because continuously I'm observing each hour, okay, like our load. Therefore, based on this one, we can predict what is the tomorrow, 10 o'clock, what is the share price. Similarly, based on our load also, when we are having several years data, several months data which is there, I can predict tomorrow at 11 o'clock what is my load. If you predict the load, what advantage you will get? Any advantage is there? If tomorrow my load at 11 o'clock something, then what is the advantage? Suppose if you take for example stock market is there. Tomorrow I will predict what is the Reliance stock price. If the price is reduced means I can purchase. I can make money. With respect to the load, if I predict something, some value, then what is the advantage? Who will get advantage in that case?
Both the markets, sir,
Markets. Huh?
and better load management, sir.
But the operator point of view, is it not?
So
Suppose
that's
the operator,
from the residential point of view, they could also plan their demand response activities, all those demand side management.
okay, demand side management, because as on today, still our consumers or customers should be
Yes,
well
sir.
educated with respect to the electricity and all that, is it not?
Yes, sir,
Based
yes,
upon this one. The demand side management will come into picture whenever we are having, suppose the night time, 2 o'clock I want to use, then cost should be reduced. Then
Yes,
everything will
yes.
works very well, is it not?
Yes, yes, sir.
Suppose
Sir.
night 12 o'clock also if you use, 2 o'clock also if you use, the price is same as that of my load is peak, then no one will bother, is it not?
Yes, yes, sir.
There we just to give some in newspapers or something, night 2 o'clock if we use, the cost of the per unit is only 1 rupee means several people will stop in the mornings, is it not?
Yes, sir.
Okay. There is some okay. Therefore, when predict the load, operator will have some advantage. Suppose my load I'm expect at 10 o'clock, my load is okay. Next day 10 o'clock, my load some 100 megawatts. But in my hand, I have only 80 megawatts is there. How to match another 20 megawatts? Whether shall I borrow from other one or shall I switch on my another generator? Like that one, he can plan. Okay. And second point, translation of a string of words into another language. Therefore, whenever we are having a string of words which are there, string of continuous words, to change in the other language also. Okay, this is. Therefore, if you see some of the examples of what is the sequence and all that, a traditional problem with the neural networks seen so far is that they have no memory. So far, the traditional algorithms, shallow neural networks or feed-forward neural networks, which is having based on the back propagation algorithm, there is no memory at all. When there is no memory, it cannot remember. Suppose when you are going for in a sequential way, you should remember the previous one. The memory should be required. Okay. Therefore, the conventional neural network, that doesn't have memory. First thing, limitation. So they are poor at using context. Okay. That is, Rama is going to school. Rama going to, the sequence should come. Randomly it is coming means it doesn't have any meaning. Therefore, so they are poor in using context. Context is important to answer questions about sequences. For example, if we are translating piece of speech, we might be considering just one word at a time. It is context that let us consider the words that came before and after. Before and after. So we can make the best translation. That is Rama going to school. Going before, what is that? Go after, going, what is there? Before and after. Then the translation also will become easy. And sequences, language examples. An important type of sequence is language. Language as a stream of letters or words or larger units like sentences and paragraphs. Making sense of the sequences is easier if we can look at the entire collection. He told me, a sentence is, he told me I could have one of these strawberries. Then we look at previous stream of words in this sentence to see who is he. He told me I could have one of these strawberries. Who is he? Okay. And one more thing, she said to wait over there requires even more context with respect to what we are talking. Context or surrounding information to be understood. Okay. The applications of sequences, because we are talking about a recurrent neural network, sequences are very, very important, where poem or story, perhaps even the voice of a famous writer, make a new scripts for TV, sitcoms. Okay, music, we can generate a whole song and single melody, polyphonic melody, or a complex song. Okay, with melody and chords. That is to generate a whole song or poem or TV. Okay, several things. Okay, lyrics, we can create song lyrics. Okay, as you will know, Chat GPT and all that, it can also do several things. And pop music, folk music, rap lyrics, etc. Speech to text systems, but okay, that also one can do. And generating captions for images and videos, as we are seeing one language, whatever the language we want, and when speech is going on, text also will appear in our videos. Okay, there are several websites are there for the recurrent neural network, in particular to the LSTM. These are some of the website of LSTM. Sorry, reporter, lyrics, rap music, how they are doing it. Okay. Hello? Hello? Okay. In this recurrent neural network, that is LSTM, this lecture presents a learning architecture that is explicitly designed to learn from sequential data. Therefore, the RNN is a sequential network. Therefore, data also should require a sequential data is required. This architecture is called recurrent neural network, or simply RNN. RNN, recurrent neural network, is often called LSTM, long short-term memory, because what is the long term, what is the short term, we can see. Long short-term memory, because that specific technique is a widely popular choice of the implementation. Because most of the time, if you want to predict anything, people will use for prediction when we are having forecasting. LSTM is very, very popular. In this lecture, we will see that makes a RNN special, how to build one, and how to use it. Okay, what is the architecture of the LSTM? Because LSTM will have each cell will be there, and several LSTMs cells we should use. Okay, but one of the most important thing is that this LSTM architecture, okay, it is somewhat complex compared with your CNN or BPA. Okay, and here shallow neural networks are very simple to understand. But when you are going to the deep neural network, if you see the even CNN also in this one, filters, how many filters we have to take, what type of filter, different designs. Okay, therefore this LSTM is still somewhat complex, but it is more accurate for a prediction point of view with respect to the load forecast or whatever it may be. And RNN is often called LSTM because that specific technique is widely popular choice of implementation. Okay. What is recurrence and what is recurrent neural network? Therefore, when talking about a recurrent neural network, we should try to understand what is the recurring. Okay. Each time it is repeating recurrent what you are talking. Recurrence refers to repeating or recurring action. That thing is will go on repeating in the name of in the name itself. A recurrent cell repeats a given operation over and over, so it is recurring. Okay, once again, a recurrent cell, okay, recurrent cell, for example, is the LSTM cell. It can be a recurrent cell repeats a given operation over and over, so it is recurring. Therefore, these recurrent networks provide us with a flexible way to add memory, because previous networks they doesn't have any memory, therefore they cannot remember, they will not bother about sequence. Therefore, but here in this recurrent networks, it should have some memory and context to our networks. That is what is the sequence and all that. Okay, with respect to what concept we are doing. The recurrent neural networks can do all the things we asked above and many others. They are used for activities ranging from language translation to automatic photo capturing and even the generation of the new prose in the style of known authors. Okay, therefore here, that is why this most of the time practical application will use deep learning networks. Therefore, wherever sequence is there, we will use the sequential networks based upon the application. Knowing this recurrent cell, because as a recurrent unit or recurrent cell, it is one thing. Only one unit will not do. Several similar units we have to connect in series. It is like a neuron, one neuron to another neuron, like that. One cell to another cell, another cell, dot, dot, 1, 2, dot, dot, n number of cells or units we have to connect. Okay. If you see, a basic artificial neuron does not have memory. Therefore, we can address the lack of memory in neuron by replacing it with more complex bit of processing called a recurrent unit or recurrent cell. Therefore, to include the memory, therefore, if you see, for example, the input is given, some internal memory is there for the RNN, then we get the output. That without memory, we cannot process the sequential data. Therefore, if this figure is that a computational unit that is capable of remembering some internal information. This internal information which is remembering, the most of the time we will use the word state. Okay, internal information over time, at some time t equal to t1, then some information is there, it should store. That information every time we are using in this one as a state. Okay, we call the internal information as a state or state of a unit. Therefore, this please mute your mic, please. Recurrent neural network uses the internal memory to process. Recurrent neural network just okay. Recurrent networks, as you have seen, it is repeating a recurring action. Recurrent cell repeats a given operation over a particular time, and recurrent networks provide us with a flexible way to add memory and context to our networks. Recurrent neural networks can do all the things we asked above and may others. They are used for activities ranging from language translation to automatic photo capturing and even the generation of new prose in the style of known authors. Okay, this we're talking. Therefore, this recurrent neural network is having the memory. Therefore, the internal memory we are calling as a state. Therefore, recurrent network uses internal memory to process its input into output, and internal memory is able to change with every input even after training is complete. Therefore, unit is special as it saves information. Each time a unit process an input, each time an unit means LSTM unit or LSTM cell. Each time a unit process an input, it uses some of what it learned from previous outputs. Therefore, in this one, once again, this recurrent layers in this recurrent unit or recurrent cell is mostly just a bunch of neurons and activation functions, because here we will use the activation functions here also, a sigmoidal activation function as well as a tan hyperbolic activation functions we will use. Okay, RNN cell is mostly just a bunch of neurons and activation functions, but they are connected or they are wired up in a specific way and treated as a single unit. Okay, and there is also a bit of memory in there, which we will see later. We just pop this unit or cell into our networks as a layer like other. Therefore, whenever talking about a neuron is there, we'll connect another neuron by means of a weight, synaptic weight. Here also what happens is that if you take one cell, only one cell will not do. The output of the cell is connected to the another cell of the LSTM, another cell of the LSTM. Like that, we will take based upon the requirement of the problem, n number of units or n number of cells we will consider LSTM cells. Therefore, we can build deep learning networks using a mixture of standard layers and layers made up of recurrent cells. If the recurrent cells are an important part of the network. We call it recurrent neural network or RNN. As you have seen, next, what is a state? Because the word which is state, which is coming into picture, we'll use very frequently. Therefore, as you've seen, this is the recurrent cell of the LSTM. Therefore, in this one, the state which is there, we are calling the internal information in the unit's memory, that is state. State equal to information we save and read in this memory. It will, information is saved in the internal memory or state is saved, both are same. State equal to remembered data that describe the situation or configuration. We can say save the state and read the state. State can be written to the file, saved on a USB or transmitted over a network. When it's saved, we can write on in a file or whatever it may be. But in recurrent neural networks, we keep the state inside the recurring unit. Okay. Okay, robot example not required. Okay. In the recurrent neural network, the state is play a vital role. What is recurring is that suppose we are giving some input, the state, and based upon this one, we are getting the output 0. Again, output of this recurrent unit is becoming the input to the recurrent RNN unit. The input is input 1 because several inputs are there. Input 0, input 1, input 2, data, input n number of inputs. Then here what I want to say is that when we are having, it is recurring every time. Initially, here when you start, it is an input corresponding state from other unit. This how this state is coming. This state is coming from the other unit. All are connected in series. In the beginning, there may not be the state may become 0 also. There is no the state input. It is a simple recurrent neural network. If you see this one, how it looks like with respect to this one, there is only one RNN unit and only one state. And they are reused by each sequential input. They are reused in each sequential input, producing sequential outputs. Okay. Sequential means after step 1, step 2, step 3, like this sequentially. And how we can manage the interpreting the state values, which is, okay, after this one, I will talk about the topology of the LSTM. Recurrent neural network manages the state for us automatically regarding reading and writing values. State information is stored inside the recurrent neural network unit itself. State is just a list of floating point numbers. Hello? Okay, fine. Fine. Okay. Okay, are you able to hear?
Yes, sir. Yes, sir.
Are you able to hear?
Yes, sir.
Okay, 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 thank you. Okay. Okay, the state, every time we use the word the state or internal information is stored in the memory. Therefore, the state is nothing but if floating point number, it can be any number of the size of 3, 5, or whatever the length it may be. Therefore, this number, okay, that I will talk later. The question is that the question, how do you interpret the numbers in the state? Therefore, what the question is, what do these numbers in the state represent? And what is exactly remembered and forgotten? Because in this one, in this LSTM, apart from the neural networks, we will, and in the neural, when neural network is there, we'll use some activation function like sigmoid or tanh function. And apart from some gates will be there. One is the forget gate, remembering gate, okay, or input gate, output gates will be, 3 gates will be there. Input gate, output gate, okay, and one more thing is that forget gate. Okay, what are those gates? We can see that here at present, what do these numbers in the state represent? What is the currently remembered and forgotten? That is why remembered and forgotten, the name of the gates, what does it exactly mean? The recurrent neural network cell decides what the state's contents. The recurrent neural network cell decides what the state's contents should mean and how to manage these numbers, so that the network as a whole ultimately produces the answers we are asking it for. Most of the time, we don't need to worry much about interpreting these state values. At present, we need not bother about what the values means. Therefore, this how it organized in the recurrent neural network. For example, when you are having 3,
Sir,
that
please
is
share the screen, sir.
screen. Okay. Are you able to see now? Screen?
Yes, sir. Yes, sir.
Okay, thank you. Okay. Okay. The organize the inputs for RNN, for example, input to recurrent neural network unit samples, for example, each sample is composed of features. Each feature is made up of time steps. Then how to organize the data? Suppose most of the time we will use the Python. Therefore, in this one, the 7 samples are there here, time steps, 3 features are there. With respect to load forecasting, for example. Therefore, what are 3 features? For example, wind speed, temperature, humidity, and 8 time samples, 9 a.m. to 4 p.m. For example, we have considered 8 samples. If you take, most of the time, you will take 24 hours. And 7 samples, what is that? Sunday, Monday, Tuesday, like that, 7 days we have considered. This is the how we are featuring. Just like in case of recurrent neural network, conventional neural network also we have seen that color data, okay? Those things, okay? That is a 2-dimensional, or we'll call color data, or it is 3-dimensional picture. Therefore, suppose we collect our 8 measurements of 3 types of data on 7 consecutive days. We can arrange our data as 7 samples, each composed of 3 features with 8 time steps per feature. Now, in the LSTM, now we are, these are all what we are discussing with the preamble to this, with required for the LSTM. More popular searches uses a kind of RNN cell with the name long short-term memory, or very popularly is known as LSTM. LSTM is so popular that when people today speak of an RNN unit, generally they often mean an LSTM. Therefore, let us see how LSTM works, or what are the features first of all. As I mentioned, in this LSTM cell, the most commonly we will use neurons as well as the gates. The neurons, as you have seen, a neuron is a nonlinear. If adding the nonlinear activation function like sigmoidal function, tanh function. Now we'll see first of all what is a gate, because I mentioned 3 gates are there: input, output, as well as the memory, as well as the forget gates. The key mechanism in LSTM is a gate. First, let us understand it, how it works. This figure shows a physical gate controlling flow of water out of a pipe. Okay, how the gate, general gate, how it works. It is completely open, gate open 100%, I'm calling. Gate open, little bit closed, gate open 75%, gate open 50%, gate open 25%, gate open 0. It is general way, what we are talking. That is picturing a gate over a water pipe. Okay. Now come back. In this one, in this figure, the figure interpreting a gate with numbers. Okay, this is with respect to water, a gate with respect to number I'm talking. Suppose the input to this one, because it's summer, okay, 1 and here 100. The bottom one is the result. Okay, that is 1 into 100, 100 I'm getting. Gate open 100%, equivalent to that. This 0.75 into 100, 75, gate open 75, equivalent to that. 0.5 into 100, 50, gate open 50%. 0.25 into 100, 25%, gate open 25%. 0 into 100, gate open 0%. Therefore, it is the analogy with respect to this pipe opening gate analogy to numbers analogy. If you see, each diagram, the input value is 100. Each one, the input value is 100. 100 is shown at the top. The gate valve is shown blue. It is a gate valve. We can control the valve. Therefore, I'm controlling with 1, 0.75, 0.5. The threading, let's say, if you assume, okay, 0.25 and 0. Therefore, in each diagram here, the input value is 100, shown at the top. The gate value is shown in the blue, and the result is in the box at the bottom. This is the results, indicating we are 100% open, 75% equivalent to that. We just multiply input value by a gate value to get back the gated value. Now, for example, I was mentioning the 3 gates will be there. One of the gate I'm talking, forgetting using gates. Okay, gate name we will call forget gate we will call. Suppose how it works. This is the symbol for this one. This is the memory. Okay, gate we will indicate like this triangle downwards. Okay, and having memory back is coming into the gates. Suppose if you see how it works, my starting memory is 1032 something, and my gates are just like what you have seen here. This is the gate 1.5. How can control? Therefore, starting memory is this much, my gate is this much. Out of these two, starting memory and gate, the ending memory is the resultant. That is 10 into 0.8, 8. 32 into 1, 32. 15 into 0.5, 25. 8 into 0, 0. 16 into 0.25, 4 line. Okay, this is symbolic one. And if you see the gate valve equal 1 means don't forget, and gate valve equal 0 means forget everything. 1 means it will remember everything. Gate valve 0 means it will forget everything. 0. Okay. Therefore, forgetting valves in memory. Now come back. Another gate is that I discussed about the gate valve. That is the forget gate. Forget means it is based on we can control 1 or 0. 1 means it will remember everything. 0, it will forget everything. Therefore, 0.5, 0.75, 0.25, 0.5, based on how much you want it will remember. One more gate name is that remembering gate, or people will call some input gate. Okay, this remembering gate. Several names are there. That is the forget gate, only one name. But remembering gate, we can use remembering gate or input gate. In this one, how it works? Here, if you see this picture, figure in this one, new values, it is the gates input is going based on new values and gate value, gated new values from this point and this memory, whatever is stored plus, it is plus sign, we are getting some resultant. Therefore, if you see these new values, there is a new value and new value, and the gates, these are some values you have considered, and summation, and it is a summer, that is we are having 8 and 0.75, it is the resultant one, that is 32 into 0, 0, 8 into 0.75, 6, 10 into 0.2, 2. From this gated new values, these are the gated new values, plus starting memory, it is, we are using the symbol sign, plus 16 plus 6, 22, 0 plus 8, 8, 2 plus 50, 50, 52. Like that, we will get the this remembering memory works, or we will call input gate also. Okay, if you see this, the process of remembering A, in this figure A, we start with new values to remember shown on the left. We may not want to remember these at full strength. So we first apply gates. Then we add gated values to the existing memory and save that back into the memory like that. Okay. The operation schematic form is shown. This is a figure B. Now one more thing, one more gate, selection gate, or we will call output gate also, we will call this one. Therefore, once again repeating, where I have 3 gates will be there. One is the forget gate, another one is the remembering gate or input gate, another one is selection gate or output gate. Okay. In this one, if you see this figure, memory and gate, the input is gate. Okay. This reverse triangle is the gate. We will use the symbol. The memory and gates input, we will get the selected values. Therefore, in the selection or output gates, to select from memory, just to determine how much of each element we want to use, how much I want to use. Therefore, if you see, for example, these are numbers what we are given to understand how it is working and all that. Memory, some values you have considered. Okay, memory. And gate, some values we have considered. Then what are the selected values? 10 into 0.4, 4. 32 into 0.25, 8. 50 into 0.5, 25. 8 into 0, 0. 16 into 0.75, 12. These are the selected values. Selected values means the output of a LSTM. Therefore, how it works, just we are talking of once again some of the building blocks of this LSTM. Therefore, selection using gates. The selection gate, another name is the output gate, what we will call. This figure here, what he has given explanation here, to select memories, we gate the values in our memory. The gated results are our selection. The output of this one, or our results are, that's why the selection gate we are calling as the output gate also, another name. Okay. Okay, with this brief introduction of these gates, states, etc. and all that, the LSTM cell, it looks like this. This architecture of a long short-term memory unit, it looks like. As I mentioned, reverse triangle, we'll call the gates. Okay, this is the remembering gate. Remembering means it is the input gate, forget gate, same, and selection gate. In selection, we will call output, because the connect with output, we will call output gate. And here, tan H indicates it is the activation function, tan hyperbolic function. And this circle A, B, C, D, which are there, these are the neural networks. And this is a state. State means we have seen information. And this is a positive sign. And here, if you see, this is one cell. It is one cell. What is the input to the cell is going? Some input is there. Another input is the previous output, because this is one cell. One cell, it is like a one neuron. Therefore, here what we will do is that, just like if you compare with the neural network, this is my neuron 1. Okay, some pens, some issues. Okay, in this is one single neuron. It is like, if you want to connect another neuron, a connection is coming into picture. Similarly here, this is one LSTM cell. As I mentioned, we should require n number of like these cells. This cell number 1, cell number 2, the output is going to the connected to the cell number 2. But it is the first cell, the previous output is always 0. After that, I will get the output, and once again input I will provide, like this process continues. Okay. Therefore, if you understood one cell, therefore the structure of the each cell is same, only connection, okay, in tandem. Therefore, this is, if you see, the input and previous output. If it is the first cell, cell number 1, my previous output is 0. Then what is happening? My input is going to this A is the neuron. Just like when input is there, some weights will be there, a weight matrix. Then it is activation from sigmoidal output. When we are having sigmoidal output, what is the output we will get? And my activation from sigmoidal output, my output is between 0 and 1. Whereas if I use my activation function tan hyperbolic function, what is my output in what range of the values I will get with the tan h? Between +1 and -1, based upon the tan hyperbolic function. Therefore, this is the input. Here weights are there. Based on the here we are having sigmoidal activation function. Based on the output I will get. Then the input to the forget gate, because the F is the forget gate. Okay. Therefore, if you see how it works, so before that I will read also the architecture of an LSTM unit. Inputs, previous output and a new input. What are the input? This is also input. This is also input. One is the previous output and a new input. Inputs. Output. What is the output? New output on right extreme. It is the new output of this one. And state memory at top of diagram. What is the state? This top of the diagram is the state. Now the triangles represents gates. Triangles, okay, represent gates. There are 3 triangles: F for forget, R for remember, and S for select. These are your gates are remembering, forget, and select gate. Gates manage internal memory and give a lot of control over what cell remembers and forgets over time. So it can manage its internal cell memory in the most effective way. The circles represent set of neurons labeled A through D. I was mentioning this circle A, B, C, D are the neurons. These triangles, F or S are the gates. Circles represent set of neurons labeled A through D. The input to these neurons is a single list formed by simply placing the previous output and the new input one atop the other. Therefore, the input is same to this neuron A, neuron B, neuron C, neuron D. Same input and previous output, both combining both here. But the weights may be different. For this neuron, the weights which will come into picture, the weight of A, weight of the B, weight of the C, weight of the D neurons may be different. Now come back. If this figure, in this one, forgetting stage of LSTM, because all, okay, only it is highlighted with respect to only forget. Therefore, how it works, if you see only one gate, because 3 gates are there, one gate I'm talking here. The previous input, previous output, if it is the first gate, previous output is 0. Otherwise, some values, some numbers will exist, and some new input I'm giving. Then here neuron, it is some weights are there. Therefore, the activation, sigmoidal activation function as given as input, and previously state, state means some information which is stored in the memory, both will come, I will get the output. Therefore, if you see combined input and previous output, are transformed by A neurons into gate signals, which then control F gate and cause some values from state to be forgotten. Forget some current state, because how much they will forget, it will decide based upon the values. Okay. These are like, if you see, with respect to some previous output, some values, input is some values, okay, some weights will be there, and sigmoidal activation functions. Based on, I will multiply, I will get the output, it is shown, symbolically it is shown. Okay. Now come back, working of a forgetting gate, how it works. Okay, it's summarized. The new input and the previous output are used by the neurons in A to create a list of gate values. Note that a sigma or sigmoidal activation function squashes each neuron's output into the range of 0 to 1. Therefore, always you remember, whenever we are using sigmoidal activation function, my output, if it comes, whatever the values may be between 0 and 1. And tanh hyperbolic, when I'm using, it will be +1 and -1. This makes it appropriate to use as a gate because it is controlling between 0 and 1. That's why we are calling as a gate. Those are then applied to the current state. Okay, that means if you see, these are your values and it is applied input. Okay, a sigmoidal activation function is there. This is a neuron and there's some state also coming to this gate. I will get based on between these two, I'm getting the output. Okay. Those are then applied to the current state. Therefore, each element in the list of values held by the state either stays the same if its value is 1 or else moves towards 0, causing us to forget some or all that value. Because as I mentioned, if the value is 0 means it will forget everything. Value is some fraction, is remembering something. If the value is 1, remembering everything. Okay. So at the end of the forgetting stage, we have a temporary copy of the state where we are partially or completely forgotten the elements in the state. That means forget some current state, some or all, entirely also. Now come back another gate, remembering gate, because you highlight only with remembering gate, remaining are not highlighted. The remembering gate, or I can call input gate, we can call. Therefore, once again, in the remembering gate, two neurons are coming, B and C. The previous input is there, previous output is there, and input both are going to B and C. And B and C will have some inputs, weights, and both are given to this remembering gate. Resultant of B and C, we are giving to this summer. It is positive. Okay. Then whatever we are getting, it is going to the state from this point. Therefore, if you see in this one, the remembering stage of the LSTM, the combined input and previous output are fed into two sets of neurons. What are the two sets of neurons? B and C. The outputs of C are used to control the remember gate R. The output of C, okay, output of C, this is the output of C, and the B is added to this remember, then both are going to for controlling. The outputs of C are used to control the remember gate R, which adjusts the values combining out of B. The result is that the input and previous output are scaled down. The result is that input and previous output are scaled down and then added to the version of the state coming out of the forget gate F. The result is then written back to the internal state. Once again, it is going to the internal state. The state is nothing but information which we are storing. Now, if you see this, summarizing this remembering gate.
We are also in charge. I'm also in charge.
Please switch off your mics, please. Working of remembering gate or input gate, another name. The stage is to remember something about the new input that is just come in and something about previous output as well. Okay, this is the C neurons. This is only summary what I discussed there. The C neurons are going to be used as a gate values. So they have a sigmoidal activation function. C neuron will have sigmoidal activation function on the end. The outputs of B are the values being gated and ultimately remembered. The gates are used to control how much of the combined previous output and current input should be remembered when they pass through the OR gate. Okay. The resulting gate values are added to the state. This new value of the state is then written to the state memory. So these values are now remembered. That is here what you have shown, the values which going to state. When state means it will remember the information. That remember some new info and add it to at the current state to get new state. Okay. The last one is that selecting gate. Okay, S is the selecting gate, or we can call output gate, because from this one we are getting the output gate or select gate. Okay, selecting gate. In this one, if you observe the input to the D neuron, we are having A, B, C, D. D neurons are the D's to the selecting gate. The inputs are same. Previous output and input are going to this D. Here some weights will be there, some activation for segmental activation function. It is going to the S gate, selecting gate. And one more thing is that from the tan hyperbolic also going to S. Based upon this two, it is going to the output. Therefore, in this one, the combined input and previous output are used to control gate S, which adjusts the new state that was generated by the remember gate. This is the cell's output sum of new state. Okay. And in this one, yeah, we are using a TANH. The advantage of this TANH, what happens, it overcomes the vanishing gradient problem, because the values will be there between +1 and -1. That's why there the question comes when you're taking neural network, neurons, sigmoidal, but why we are taking TANH is that to overcome the vanishing gradient problem, and convergence is faster. Now to summarize the working of this selecting unit or selecting gate or output gate. Finally, we select some of this newly computed state for output. Okay. We run the previous output and current input into another set of neuron marked D, which also have sigmoidal activation function. We use the output of the D neurons as gate values in the gate marked S. Okay, S is the selecting gate. Therefore, the input to this gate is the new state we just computed, but first we run that through a TANH function. The TANH function is the same S-shaped function that we saw when this. Okay, this is the case, and the TANH function squashes. Okay, it limits the state values just be in the range +1 and -1. Those values get gated by the S gate and then become the output of the LSTM cell. Okay. Okay. Therefore, if you recap, the summary of the LSTM is that we have seen 4 neurons are there and 3 gates are there. 4 neurons we have seen with LSTM cell A, B, C, D. Each one will have some different weights will be there. And one more thing is that they will have sigmoidal activation function we are using. In case of the gates a forget gate, it will based upon the controlling the gate, how much information it will forget, we will decide. And similarly remembering as well as the output gate. Therefore, the summary of the LSTM is that LSTM takes the previous output and the current input and combines them. The input is not single input, two inputs are becoming one input. That's why previous output and current input. The combined signal will be used to form gate values and will also get remembered. The first step is to forget some of the current contents of the state by running it through the F gate. F is the forget gate. The second step is to remember, okay, after forget gate, remember gate or input gate. The second step is to remember or input some of the new information by running through the OR gate and then adding that result to the state. The result of that becomes the new state. What is the third gate is that select gate or output gate. The third step is to select some of that new state to present as output by running through the S gate. Therefore, in this way, what is happening is that in this way, LSTM can remember information indefinitely. LSTM can remember information indefinitely by not forgetting it and then not adding to it. Okay. Or what it will do? LSTM can completely forget some information and replace it with new values. or LSTM can partly forget some information and then partly remember some new values along with them. It can do because based upon this LSTM cell, one cell, it can do either this or this or this. Therefore, this type of information you will go further, you will use n number of LSTM cells we will use. Okay. Okay. Here one more, just how is forgetting, remembering, and selecting all done. Okay, in this one, we are in 3 gates are there for forgetting, remembering, or input gate, or selecting gate. How it is done? The explanation is that the 4 sets of neurons labeled A, B, C, and D control all this forgetting, remembering, and selecting. All of their weights are learned using gradient descent. What is the gradient descent? It's like back propagation. Okay. All their weights are learned using gradient descent like any other weights. Eventually, the LSTM learns values for the weights that allow it to forget, remember, and thereby select the right information at the right times to give us useful results. And some more information on this LSTM. The name LSTM. Please mute your mic, please. The name LSTM comes from thinking about what is going on inside an RNN cell, LSTM cell or recurrent neural network cell. Recurrent neural. Hello, please mute your mic, please. Hello.
Optical communication, machine learning is very good. So high impact factor.
Okay, this recurrent neural network cell has some persistent or long-term memory in the form of its state. Okay, why you are calling? We are named it's a long, short-term memory. Then what is a long-term memory? In the form of its state, and state can hang on its values from one input to the next indefinitely. One input to another one. Therefore, this cell also has some short-term. There are some short-term memory and long-term memory. Therefore, we are calling as a LSTM, long short-term memory. The short-term memory in the form of the neuron output, short-term, where the long-term memory in the form of we'll get in the state. That is why name LSTM. The cell has some short-term memory in the form of the neuron outputs. These numbers are temporary and exist only during the processing of new input. Because normal neurons, they doesn't have any memories as a single neuron if you consider. They are replaced with new values when a new input arrives. Therefore, the goal of LSTM takes some of these short-term reflecting values and give them a longer lifespan, allowing them to contribute to future calculation. That is why for the prediction, it is the best example. Thus, the short-term memory is being given a longer life, resulting in the name long short-term memory or LSTM. Thinking of LSTM instead as persistent or short-term memory. Okay, some more notes on this LSTM is that each recurrent neural network cell contains some memory to hold its state. Therefore, the shallow neural networks doesn't have any memory. Therefore, to process sequential, it requires some memory. The state is usually just a list of numbers. Every time you state or information, whatever it may be, some numbers, as you discussed in the beginning. The cell memory is initialized with default initial values before the first input arrives. Those values change as inputs are received and the cell memory is updated. Therefore, the cell memory can also forget information that is no longer necessary. The cell memory also can forget. That's why we are forget how much it should forget. Entire you should forget, partially based on the control gate, based on the gate. That is all under control of neurons located inside the LSTM. The beauty of the whole system is that with enough training, the weights in the neuron inside the LSTM unit learn to adjust themselves. పెన్స్ రావట్లేదు వెంకట, వస్తుంది. Pens. అదే ఇప్పుడు మనం రాయాలి అంటే పెన్స్ కనబడుతుంది. పెన్స్ రావట్లేదు. Okay, within 10 minutes, 5-10 minutes, I will stop. Okay, but I'm summarizing actually. Remember that once the weights in the internal networks have been learned, they backprop, they don't. Okay. But when the unit is evaluating new data, these networks control the cell memory, which does change. So cell memory or state changes. Okay, there another one is the another variant of this one is the GRU, but I'm not talking GRU. If you see once again in this recurrent neural network, to summarize, just if you try to understand, recurrent neural network unit is able to remember new information after training has completed. That is, unit keeps changing after training is over. The key idea here is that memory that we refer to above. The kind of memory we are talking about is different because it changes when the network is developed, it is deployed, and in the actual use. The recurrent neural network itself will learn what it needs to remember and how. We just have to set up structure to enable it to do the job. Okay. Okay. Once again, to summarize, as the gates used in the forgetting gate, remembering gate, or input gate, selecting, or output gate. Okay. Okay. This is about the structure and how it works. I discussed. The last one, that is most of the time, I will at the end of my lecture. Okay. This is my last lecture. Therefore, I will use, that is one thing. If you are having hammer, if you are having hammer in your hand, everything looks like a nail. What do you mean from this one? If you have, if you have, or if you, or other way, if you have hammer in your hand, everything looks like a nail. What is the meaning of this one? Anyone can tell? The meaning simply it says, if you're having hammer in your hand, everything I want to nail it down. Suppose, for example, generally I will give an example. A student who are studying in hostel, if they come back to their home, what mother will do? Mother will prepare delicious foods, which he or she likes. He or she, they will eat 2 days, 3 days. Okay. After they will watch TV, enjoy 2 or 3 days. After that, boring. In the house somewhere, they found some hammer. Then what they will do? Because there is no work, they will take that hammer. They will see on the table or chair any hammer, any nail is coming out. No. And they will see on the door, on the walls, any nail is there. Because as than today, we cannot find. No, nails are not there. Even though when nails are not there, just this hammer is there in his hand, just he will nail hammer on the table or chair, whatever it is. This is general. But with respect to our artificial intelligence, what it means? The meaning of this one is that to correlate with our FDP, the hammer is nothing but your AI techniques. Hammer is AI techniques, different. Your back propagation or radial basis function or convolution neural network or LSTM or whatever it may be. Then what are the nails? Nails are nothing but your problems. Suppose when a problem is, suppose you're studying something or you want to do some research and all that, someone has done with some back propagation algorithm. or some other thing. This immediately should strike how I can overcome, how I can get the better results than this. How we can decide if you're having a hammer? What is the hammer? If you know different AI techniques, then, oh, it is not that, I can make use of this one like that. Therefore, here, with respect to our FDP, hammer is the different algorithms of the artificial intelligence. Nail is nothing but to solve the problems by using the AI. Okay, I will stop here and Venkatraman will continue. Still, if you're having any doubts, general doubts or based upon this one, you can ask. And you have applications, Venkatraman will explain you. Therefore, any doubts you can ask. Okay. Okay, it is unless you work, it is somewhat complex, this LSTM. Okay. Anyhow, at any time, you can call or you can email to me. Okay. I will try to answer. Okay. Thank you very much, all of you, for your patient hearing it out. Thank you very much.
Thank you, sir. Thank you very much.
The pen is local medicine much better. Okay, double much. Okay, man.
Yeah. Good afternoon to all of you. So welcome to last session for this faculty 1 week faculty development program. Can you please confirm my voice is audible to you?
Yes, sir.
Yes, sir.
Thank you. Thank you very much for the confirmation. So first I am trying to discuss about the dimensionality reduction and how autoencoder can be used for the dimensionality reduction. And I'm trying to explain the very, very simple autoencoder because I'm the student of Professor Vinod Kumar sir. What I learn from him is if we are trying to learn some new model or some new algorithm, you try to do some hand calculations with a simple way, in the simple way. So if I explain autoencoder model with a high complex autoencoder model, it is very difficult to explain with hand calculations. That's why I'm trying to explain the autoencoder, a simple autoencoder with some hand calculations from some derivations. Later, I'm trying to build the real-time huge autoencoder model for the dimensional reduction using the Python. Okay. So the first move to dimensionality reduction. So what mean by dimensional reduction? Now we will discuss. So dimensionality reduction. So what mean by dimensional reduction? So dimensionality reduction is a technique used to reduce number of features in the data set while retaining as much of the important information as possible. So let's assume your data set, in your data set, you have the huge number of features. And because of the huge number of features, you have some limitations, some problems. So what are the problems we will discuss? So what I'm trying to do is, if I have a data set which contains huge number of very high number of features, not samples. I'm expecting more samples, then only my model will perform well. Now, every data set has the two things. One is a sample, that means number of rows. Another is the feature, that is the number of columns. Dimensional reduction mainly focusing on the number of columns, nothing but the number of features. So if you have a huge data set in terms of the huge number of features, so with that huge data, with that huge number of features, if you train a machine learning model or deep learning model, it may not perform well. In such case, what we will do is we're trying to reduce the dimensionality. We are trying to reduce the number of features from the data set and without losing the important information from the data set as much as possible. Hope you understand what I mean by dimensional reduction. So dimensional reduction is nothing but the we are trying to reduce the dimensions of the data set. In other words, we are trying to reduce the number of features in the data set without losing the much information from the original data set. So that is called as the dimensionality reduction. So in other words, it is a process of transforming high dimensional data, that means high features data, into lower dimensional data, that means lower space data or lower feature data. And it preserves the most of the information available in the original data. That is very important. So when you are compressing your data, when you are reducing your data, when you are reducing your dimensionality, make sure that you will not lose most of the information. So definitely you will lose definitely you will lose that information. The information what is available in your original data set may not cover complete information in your compressed data set, but make sure that the loss of information not large, very small, that's fine. So that's called dimensionality reduction. So this can be done for a variety of reasons. Why we are going to go for the dimensionality reduction? The reasons are to reduce the complexity of the model, and also to improve the performance of the learning algorithm. And also, when you have a very huge data, very huge number of features, it is very difficult to visualize your data set. Very difficult to visualize the data set. So when you are compressing the data, then you are able to visualize your data set features, how they are performing, what is the relation between the multiple features, all the things can be visualized easily. I'm trying to explain in detail about to reduce the complexity of the model. What mean by the reduction of the complexity of the model? Now, I want to tell one thing. So I hope you are aware of ANN already. So I'm trying to work with the same problem what we discussed in the yesterday. So I'm trying to forecast the load. How many features are there in my yesterday's problem? I have the total 10 input features. Okay. And we have the one output neuron, that is L of T. We have the only one output neuron, right? And let's take, I'm considering the only one hidden layer. Let's assume I'm taking one ANN model, single hidden layer. And this is not a thumb rule, but let's assume generally we are following. So let's assume I want to take the number of hidden neurons in that hidden layer equal to 1.5 times of my input features. So 1.5 times of my input features is nothing but the 10 into 1.5. So how many number of hidden neurons will be? The number of hidden neurons will be equal to 15. Now, what about the complexity of the model? What about the complexity of the model? So complexity of the model is nothing but the number of model parameters. The complexity of the model is measured in terms of the number of model parameters. So model parameters means what are the model parameters? One is called weights, another is called as the bias parameters. Weight parameters and bias parameter. Now, what about the
లోపల నుంచి వచ్చేటప్పుడు అది అట్లా తట్టుగా ఉంటాయి బయట నుంచి వచ్చేటప్పుడు.
So what about the weight parameters? So what will be the weight parameters between the input layer and hidden layer? So what about the weight parameters between the input layer and hidden layer? I think so the number of input features equal 10, number of hidden neurons equal 15. So number of weight parameters equal to, so 10 into 15, that's equal to 150. So 150 weight parameters between the input layer and hidden layer. And how many number of weight parameters between the hidden layer and output layer? That is the number of neurons in the hidden layer equal to 15, number of neurons in the output layer equal to 1. So total number of weight parameters equal to 15. That's equal to 165 weights are there in this model. Okay. Now coming to the bias parameter. So how many bias parameters are there? In the hidden layer, we have the 15 neurons. So we have the 15 bias parameters. In the output layer, we have the 1 neuron. That is the 1 bias parameter. Total 16 bias parameters. So what about the total number of model parameters? Total number of model parameters equal to 270, 281, 280. No, not 280, 181. Okay, 181. So 181 is the total number of model parameters. So the complexity of the model is measured in terms of the number of model parameters. So in this ANN model, the total number of model parameters equal to 181. Okay, next. Now I'm applying the dimensional reduction. So based on the dimensional reduction technique, maybe multiple techniques are there. So any of the using the dimensional reduction technique. Now I am compressing my input data having the 10 features into 4 features. I am compressing my data. The data contains maybe 10,000s of rows, 10,000s of samples, but 10 features. 10,000s of rows are nothing but the 10,000s of samples, but I have the 10 features. Now I'm trying to reduce the dimensionality of the data set. The dimensional reduction is nothing but the reducing the number of features. Now, based on the dimensional reduction algorithm, I'm trying to reduce the 10 features to the 4 features. So now number of neurons in the input layer equal to how much? So number of neurons. Now the input features in my data set, the input features are reduced. Previously, let's assume my data set contains the 10,000 samples and 10 features. So this is my size of my data set, 10,000 across 10. Now I am reducing the 10 features into the 4 features using one-dimensional reduction algorithm. Now what will be the size of my new data set? 10,000 divided across 4, 10,000 rows and 4 columns. The features are reduced from the 10 to 4. Dimensionality of the data set is reduced from the 10 to 4. Okay. Now number of features in my new data set equal to only 4. Number of input features in my new data set is equal to only 4. So if it is only 4, the number of neurons in the input layer equal to 4 neurons in the input layer, 4 neurons in the input layer. And as per our thumb rule, what we are following, 1.5 times. So if you take 1.5 times, how much? 4 into 1.5, that's equal to, so how many neurons will be in the hidden layer? That's equal to 6. Definitely, I am going to predict the only one variable, that is a 1 neuron. Now, in this new architecture, in this new ANN model, now what about the complexity of this model? You can say, so complexity of the model. So what about the complexity of the model now? So now complexity of the model again measured in terms of the model parameters, nothing but the weight and bias parameters, right? So now what about the weights between the input layer and hidden layer? Here 4, here 6. 4 into 6 means, so between input layer and hidden layer, total number of weights equal to 4 into 6. That's the 24. Plus, what about the number of weights between the hidden layer and the output layer? That is the 6 into 1. That's equal to 6. The total number of weights equal to 30. And now coming to the bias parameters. So total number of bias parameters in the hidden layer equal to, because I have the 6 hidden neurons, so it is a 6. Plus number of neurons in the output layer equal to only 1. So plus 1, that's equal to 7. Now total number of model parameters equal to 37. You can see now. So because of this dimensional reduction, the complexity of the model is reduced in terms of the model parameters. In my original model, before applying the dimensional reduction technique, the total number of model parameters equal to 181. But after applying the dimensional reduction technique, the total number of model parameters equal to 37. So that is the advantage of the dimensional reduction techniques, dimensional reduction. So dimensional reduction can be help you to reduce the complexity of your model. Complexity of your model. Next. Now coming to the dimensional reduction technique. So the high dimensional data can lead to overfitting. When the complexity of the model increases, so when the dimensionality, if the data set has a more number of features, definitely the complexity of the model increases. When the complexity of the model increases, there is the possibility of the overfitting. That's simple. See, generally, when we go to a tailor for stitching a shirt, then he will take the measurements at some points only, maybe from the shoulder to this arm and around this arm. So only few readings, few measurements only he considered, and he will stitch accordingly. He will not take the readings, very centimeter by centimeter readings, he will not take. If we take very small measurements also, then the number of features increases, and based on that feature, if we stitch my shirt, then my shirt will be very tight. I can't move either side. It will be highly fitted, over fitted. Okay, that in the same manner. So if the number of features in your data is increases, definitely the complexity of the model is increases. When the complexity of the model is increases, then there is the possibility of the overfitting. So to avoid that overfitting problem, you may reduce the number of features by using the dimensional reduction technique. So you can convert your high dimensionality data into the low dimensionality data. And what are the different type of dimensional reduction techniques? So we have the feature selection techniques and we have the feature extraction techniques. You have feature selection technique and feature extraction technique. So what mean by the feature selection and what mean by the feature extraction? Now we are trying to see. So what mean by the feature selection and what mean by the feature extraction? So feature selection. So feature selection means, let's assume I have the 5 input features, X1, X2, X3, X4, and X5. So these are the 5 input features and I have the multiple rows. I have the multiple rows, right? Now, now I want to apply the dimensional reduction technique based on the feature selection. Feature selection means we are selecting the more appropriate features. We are selecting the more appropriate features. So that selecting the more appropriate features based on our common sense also. Suppose you are taking the data, you are collecting the data from the client and the data containing the thousands of or hundreds of features. And maybe you personally, based on our common sense, we can easily identify the few features may not have a high impact on your prediction variable, may not have a high impact on the prediction variable. Then what is the use of keeping those features? In such scenario, you can drop those features and select the more appropriate feature for your prediction. Hope you understand. That is called feature selection. Feature selection means selecting the available features in the data set. Select more appropriate features from the data set. That can be done based on our intellect or based on our common sense. So that means, so you are working for a problem and your client give a huge amount of data and that data contains a huge number of features. And you have to apply, you have to think, you have to discuss with your team, you have to apply your common sense, you have to apply your intelligence and decide whether every feature has how much impact on the prediction variable. Really, these have impact on the prediction variable or not. Yes, right, I will tell, sir. Just I'm starting now, I will tell that also. So, so that is the analysis part. Okay, so then we can analyze. So this feature is not sufficient, and this feature is not sufficient. Then you can drop those features. Then definitely the dimensionality of your features will be reduced. Okay, and second thing is called, and another approach is called, we are trying to identify the correlation between your features also. Correlation between means, so what will be the correlation between the X1? So you have to apply correlation X1, X2, X3, X4, X5, different approaches. So I'm telling one thing, X1, X2, statistical approach, I'm telling one of the statistical approach. So based on the correlation, also you can do the feature selection. That means what will be the correlation between the X1 and X1? So that correlation will be 1, definitely, because between the same features, you will get the high correlation. That means with X2, X2, you have the high correlation, X3, X3, you have the high correlation, X4, X4, you have the high correlation, X5, X5, you have the high correlation. Okay. Now, also you have to calculate what would be the correlation between in Python, in MATLAB, you have the multiple functions are available to calculate the correlation between the multiple data samples, multiple distributed samples. So calculate the correlation between the X1 and X2 and calculate the correlation between X1 and X3. So similarly, you have to update this matrix, correlation matrix. And now you have to take some threshold value. Maybe you can take the 80% threshold value or 75% threshold value. So if the correlation between any two features is more than 80%, that means the two samples, the two features are almost similar. If the correlation between any two are, why the correlation between the X1 is the 1? Because these are the same samples, right? So similarly, if there is a high correlation between any two samples, then no need to take the two, if there is any high correlation between the two features, okay, if there is any high correlation between the two features, okay, then you can drop any one of the feature. There is no use. If both features are almost similar, then what is the need of taking both at a time? Suppose if I'm working on a project, I require a developer, I require a testing engineer, I require I require a developer, I require a test engineer. In my team, I have 2 persons, 2 are the developers only. What is the need? So I can send one of my developer from my team to another team, and I take some testing person from the other team. So if they say, I hope you understand. So like that, you can reduce you can drop a few features and you can select some features from your data set. So like that also you can reduce the feature selection. That also you can reduce the feature based on the feature selection, you can reduce the dimensionality. So that is called the feature selection, selecting the features, more appropriate features from the available ones. That is called feature selection. And another one is called as the feature extraction. Another one is called as a feature extraction. Feature extraction. So feature extraction means, so from X1, X2, X3, X4, X5. So we are, from all these data samples, we are extracting some new features like Y1, Y2. Only few features will be extracted from the original features. Hope you understand, right? So whatever the information is available in this feature, so almost that will be covered here also. So we are not selecting the existing features. We are extracting we are developing the different features, but the number of features will be less when compared to your original one. That is called feature extraction. We are extracting some new features from the large number of features. So feature extraction means we are trying to extract a less number of features from a huge number of features without losing the much information. Again, I am saying that when you are going for the dimensional reduction, definitely you will lose some information, some data you will miss, and make sure that it will not have a much impact on your machine learning model or deep learning model performance. So I hope you understand feature extraction. Feature extraction means extracting the new features from the available large number of features. Feature selection means selecting the few features from the available features. So that's the feature selection and the feature extraction. So feature extraction, we have the different methods like principal component analysis. Sometimes we have used the random forest also, and we have the factorial analysis, and we have the autoencoder also. We have the autoencoder. So these all are called as the different techniques that can be used for the feature extraction. That means extract the new features from the existing features. And now, so what are the advantages of dimensional reduction? So this can be used, it helps to data compression, hence it helps to reduce the data compression. Hence, definitely, then the model parameters are reduced. So you can, if you want to deploy your model, if the model parameters are less, if you are using the ANN, if the complexity of the model is reduced, it means number of model parameters is reduced. And now if you want to deploy your model into some mobile application, as your complexity of the model is reduced, as the number of model parameters reduced, definitely the amount of space required to store the data also reduced. Okay. Hope you understand. So amount of storage required, amount of memory required to deploy my model, definitely it reduced. Then it is that is one of the advantage. And the second one is it reduces the computation time. Definitely it will reduce the computation time because number of model parameters is reduced. It reduces the computation time. And also it helps to remove the redundant features. Similar features it will try to reduce. And it improved for data visualization. And also it will help to prevent the overfitting problem. And what the disadvantage of the dimensional reduction is, as I said multiple times, one of the main disadvantage or limitation for the dimensional reduction is there is a possibility that maybe some part of information may miss from your original data. It may lead some amount of data loss, and it is difficult to understand the relationship between the original features and the reduced dimensions. So main thing is there is a possibility of the loss of some information from the original data. So which leads the loss of some accuracy in your lightweight model. It's called a lightweight model, the model which was developed based on the lower space or lower dimensional data. But you have to trade off. If the loss of accuracy is not a big, then you can go for the dimensional reduction. Because of the dimensional reduction, the performance of the model is degraded very highly, then don't go for the reduced dimensions, reduced data space or low dimension data space. That is very important. So I hope you understand what I mean to say. So when you are reducing your data set in terms of the number of features, so there is a chance of loss of some information. Because of that loss of some information, the model which was trained on the low dimensional data set may lose some amount of accuracy. But make sure that the loss of accuracy is not a big, it may be very, very small, then you can go ahead. If the loss of accuracy is very high, then you have to think about your reduced data set or low dimensional data set, because ultimate goal is you have to build a model with the highest accuracy, good accuracy. Okay. So hope it is a clear with the dimensionality reduction. Yes, sir, Kiran sir. I hope it is clear, right? We can also use the covariance or correlation between the features to select the more appropriate features for our data set. Right. So next is coming to the autoencoder.
Sir, excuse me.
Sir.
Sir, actually, if we have some 10 features and we are actually trying to predict one variable, there is one target variable is one. So can we check how these 10 features are the covariance between these 10 features and the target variable, and see which are least affecting these targets, so that we can remove those features? Can we do that, sir?
Right, sir. Actually, I am not incorporated in this presentation, but
Okay,
actually, when I'm submitting, say your doubt only, when I'm submitting one research article, then the reviewers are asking me, so try to analyze the impact of every feature on your output predicted variable.
Yes, sir. Yes, sir.
So actually, I forget, but I will share with you, sir.
Okay,
there
sir.
is one in Python. There is one library available. So that
Okay, sir.
library will give the some impact. What will be the impact of the every feature on the predicted variable based on your model?
Actually, we can use heat map also, I hope, sir. We can use heat map also. Heat map
Correlation, sir. Heat map means the correlation, right, between the features.
Okay, sir. Okay.
I will show you, but actually I also draw the heat map. The heat map means that will give the high correlation with the different colors, low correlation with the different color. That's the heat map, right?
Yes, sir. Yes, sir.
So
So actually, I am thinking that we can also generate a heat map with our target variable as a column, and rows as features actually.
Right.
Okay, sir. Okay. Please carry on, sir.
That's also that heat map. That map is called as the picture representation is called as heat map, but
Yes,
the
sir.
backend is based on the correlation, the covariance between the multiple features only.
Yes, yes, sir. Yes, sir. Yes, sir.
Yeah.
Okay, sir. Thank you. Please carry on.
So just 1 minute. Some noise is coming outside. That's why I keep mute.
I think a convocation rehearsal session.
Yeah. So this is the architecture of the autoencoder. So autoencoder is a branch of neural network, which basically compresses the information of the input variables into reduced dimensionality space. And then it recreates the input data set to train all over. So this is the general architecture of the autoencoder. If you understand the ANN, the autoencoder is very easy. So this is my input features, and this is my input layer, and this is my output layer. Actually, in ANN, at the input layer, we are giving the input features, and the output layer, we are giving the predicted variable, the variable which you are going to predict, that value will be given, target value will be given, right? But in case of the autoencoder, in the input layer and the output layer, we are giving the input features. So if you have x1, x2, x3, x4, x5, x6 like that, and here also same input features we will give. So your input and output will be remain same in case of the autoencoder. Next, what we will do is we will take the multiple hidden layers between these two. That multiple hidden layers will be taken like that. This will be like a mirror image. This will be like a mirror image. Let us assume this is the 10 features. It may be 9, it may be 8, it may be 6. Again, it may be 7. Sorry, 10, 9, 8, 7, again 8, 9, and 10 back. But it's not mandatory. Okay. So you can play with the number of hidden layers, but in generally, it is like a mirror image. Then what will happen is these input features are converted into low dimensionalities at a code space. And again, this low dimensionality features at the code space revert back to your original back. So that means from here to you get the code features. From these features, again, you are getting the original feature. That means instead of your original features, you can use the features which are available, which you are get at the latent space or the code space. So that means the values which are coming at this code space is used as a reduced features, and these are your original features. So I want to repeat once again, these are the 10 features, and output also we are giving the 10 features. Suppose if these 10 features compress it to 3 and 3 back to say 10 again, then instead of these 10, I can use these 3 only, because these 3 back give the same features. That's why, so this is the how auto encoder is working. So at this code space, we are taking the features values which are available at the code space, we are using for our as a input features for our next models. So this is only for the dimensional reduction, not your prediction purpose. And here we have the two parts. One is called as the encoder, another is called as decoder. Encoder means, so encoder is called as the encoder. So this is called as encoder, and this is called as the decoder. This is called as the encoder, and this is called as the decoder. And in between, you have the code space where you can find the reduced or compressed features. So now, so encoder is a feed forward. Definitely, it is a feed forward, fully connected network, fully connected neural network that compresses the input into a latent space representation, that compresses the input into a reduced features. Your encoder will compress the inputs into reduced features. Okay, and encode the input image as a compressed representation of the reduced dimension. That's it. So your encoder will reduces the input features into the low dimensional features. Whereas the decoder, what it will do? The decoder will extract and revert back your original features from your reduced features. Our decoder trying to revert back your original features from your decoded or your encoded features or reduced features. So then what it means is, so whatever the input, that will be compressed to code, and code revert back will give the original values. Then you can use these code instead of either input or with the output, because it will give the both. It will have the same features. If you use these 3 features, it will give the same these 10. So instead of using this 10, you can better to use this only features which are available at the code, at a middle layer, at a bottleneck. This is called as a bottleneck. This is called as a bottleneck place. In the bottleneck space, what is available, we can use those things only. So this is about the autoencoder. Code means this is the part of the network contain the reduced representation of the input that fed to the decoder. Because code is fed to decoder, and this is the reduced space. And decoder. A decoder also feed forward neural network, similar to encoder, but it is the exact mirror of the encoder. But exact mirror is not a mandatory. It's not a mandatory. You may change the hidden layers, you may change the hidden neurons, but ultimate goal is whatever the input you are getting, you have to get the output as much as possible. Then only you will get the features which are represent the almost similar information as your input. So this is called as your autoencoder architecture. Coming to the process, how it will work. First, the input passes to the encoder, okay, and produces the code. Code means low space or low dimensionality features will be produced. Okay. Next, the decoder, which has a similar ANN architecture, that produces the output only using the code. Code means low dimensionality data, low number of features. It will produce the output. The goal is to get the output identical to your input. Our goal is, while training, your goal is your output should be almost identical to your input. Okay. And decoder architecture is a mirror image of the encoder, as I said earlier. So it is a decoder architecture is a mirror image of the encoder. Okay, mirror image. This is not requirement, but typically is the case. Typically we will use mirror image, but don't think that you require compulsory. No, our ultimate goal is you have to get the output same as your input. Okay. The only requirement in the dimensionality is input and output needs to be same as much as possible. Don't expect exactly you will get, but you try to get as much as possible, same information. Okay. And you can play anything in middle. Anything you can middle in between, but ultimate goal is your output almost should be equal to your input. And what are the hyperparameters here? Your code size. So while building the autoencoder, you have to tell how many number of features you want to compress. So you want to compress your input up to what, how many number of features that you have to tell. And you have to tell a number of layers. You want to use how many number of layers in the encoder as well as in the decoder. And number of nodes in layer. Now, how many number of nodes you want to keep in every hidden layer, that also you have to tell. And also the loss function. Which loss function you want to use? Generally, we will use the mean square error for a numerical data. So as a loss function while training the autoencoder. So this is all about the autoencoder architecture. So is it clear? I think, can you, if you have any doubt as of now? But I'm trying to explain with a sample calculation, but I don't want to take this huge autoencoder. I'm trying to take very, very small autoencoder. Then I will explain. I'm trying to explain how algorithm will work, how training will work, and I want to write the code in the MATLAB. And later, with high data, huge amount of data, I want to write the code using the, I want to show the code using the Python. So up to now, autoencoder, is it clear? Okay. So only
Sir,
one question I'm asking. Actually, in case of the autoencoder, so here we are giving the input and we are collecting the output from here. Okay. So generally, in case of the yesterday's problem, load forecasting problem, in the output, we are getting some prediction and we are comparing with the target, right? And now tell me, in case of the autoencoder, what will be the target values? What will be the target value, sir?
Input features.
Yes, sir. So your target values will be input feature because I'm trying to get the output same as the input. So I am trying to get the whatever the output is coming, I want to compare with the input. That's it. So thank you, sir. So
Sir,
this is about the
sir,
architecture.
excuse me, sir.
No, sir.
Sir, I have a small doubt. Sir, you are giving the input features and you are taking hidden layers and you are getting the latent space code or the reduced dimensional data you are getting.
Right.
So whenever we want to reconstruct the data using this reduced dimensionality or latent space data, so does the model know about the input features? How does this happen actually?
I will explain, sir, that.
Okay, sir.
So we will I will explain some algorithm. Maybe
Okay,
you will
sir.
get some idea about that one.
Yes,
Okay.
yes, yes.
That's why I'm trying to explain very small architecture, very small architecture, only for understanding purpose only. I am trying to explain with that small architecture. How it will work, it's almost, if you understand the ANN, then it is very easy to understand the autoencoder also. So let's assume, for example, I'm taking only for demonstration purpose. I have the three features, X1, X2, X3. I want to compress these three features into a single feature, X. Let's assume. Okay. So then I want to use the autoencoder. So I want to use a very, very small autoencoder. Don't expect you will get the exact better performance, but only for the demonstration purpose, I'm taking a very small autoencoder. Now, based on this analysis, how many number of neurons will be in the input layer of autoencoder? It will be 3. So this is the X1, and this will be the X2, and this will be the X3. So let's assume I want to, instead of 3, I want to extract the one feature that is called Y. Let's assume. Instead of 3 features, I want to compress these 3 features into a single feature that is called Y. Okay. Now this is the one. And now I don't want to use the multiple hidden layers in between because it's difficult to explain with hand calculations with a derivation point of view. But same thing will be happening with the multiple hidden layers also. So then I want to use the one code in between. So in code, how many number of neurons will be? In code, how many number of values, how many number of neurons we have to keep here? Only one, because I want to extract only one feature from the 3. From these 3 features, I want to extract only one feature. So that's why I want to keep the only one hidden neuron. Okay. Now this is called as your encoder part. This is called as your encoder part. I'm not using the multiple hidden layers in between for only for easy of understanding and easy of analysis. But actually you can keep the multiple also. Now this is called encoder. Now decoder. So from this code space, you revert back to expect the same number of output features. Again, your output layer also has the 3, and from this output layer you have the outputs O1, O2, and O3. And we are comparing this O1, O2, O3, which values we are trying to compare this one with
X1, X2, X3.
X1, X2, X3. That means we are expecting, we are getting the same output. We are getting the output same as the input. Okay. Now you have to keep the fully connected. Now you have to keep the fully connected. Now we have to keep the fully connected. Okay. And here you just for what it's called for demonstration purpose, I am assuming that I have the linear activation function everywhere. I have the linear activation function in the output layer and the input output layer and the hidden layer are the code space. Okay. So this is called as the encoder and this is called as the decoder. Okay. And now, so actually we have the bias parameters also, that also I'm neglecting for this mathematical derivation point of view. So now the weights between the, let's assume this is the ith layer and this will be the jth layer and this will be the kth layer. Okay. The weights between the ith layer and jth layer is called as the wij, and the weights between the jth layer and kth layer is called as the wjk. Okay. So now let's assume I'm giving the first sample, 1, sample 2, sample 3. If I'm giving a sample X, so how it will work? First, forward propagation. So forward propagation means now you have to calculate the output of your code. So what is the output of the code? Oj equal to output of the code. Oj equal to your weights into input. So weights are wij into X. So you got the output of the code. Now this output of the code is the input for your output layer. So then what is the output of the output layer? So output of the output layer, that's OK equal to, you can write the weights here, wjk into, what is the input for this layer? Output of the hidden layer or output of the code space. So that's called Oj. So now I have the OK. OK means O1, O2, O3. But actually I am comparing with the original values, input features X. Input features X, right? Now calculate the mean square error. So what is the mean square error? Mean square error E equal to sigma k equal to 1 to number of neurons in the output layer, that is called capital N. And what is you are expecting? X. And what you are getting? OK. So this is my desired target value. But I am getting the OK, output of my output layer, whole square. Okay. And the mean value. So mean value means 1 by n, because average of square error between each neuron. For each neuron, calculate the square error, add it all and divided by n, that will give the mean square error. And I will keep the by 2. I think Vinod Kumar sir told why you keep the by 2. But if you don't want to keep the by 2, it will have some, learning it will be increased. Okay. I don't want to touch that part again, but I think you know about this one. Now I have the mean square error. So once you got the mean square error, that's what we have to do. In the forward propagation, we calculate the output of the output layer and we calculate the mean square error. In the backward propagation, we are trying to update the weights. So how we update the weights? We have the wjk and we have the wij. How we calculate the delta wjk? So delta wjk equal to minus, based on the gradient descent algorithm, eta, that's called learning rate, dou E by dou wjk. So what we have here, from here, what we have? So you have to differentiate E with respect to wjk. So wjk can be visible in the OK. So what is the differentiation for this one? So actually we have the minus sign here. Here we have the minus sign. When you take the differentiation, this minus will be cancelled. So eta. And we have the by n. And this 2 come forward. 2 will be cancelled. So what we have? X minus OK. And OK with respect to wjk. If you differentiate OK with respect to wjk, what is the resultant differentiation? Oj. So that is called as the delta WJK. Once you got the delta WJK, now update the WJK equal to WJK plus delta WJK. So this is how the weights between your code space, your output layer will be updated. Okay. In the same manner, so how we can update the weights between your code space and with your input or input layer? How we update? So what are these weights? Wij, right? So you can write it as a delta Wij. So that's equal to delta Wij equal to. So how? To the minus eta dou E by dou Wij. So tell me. So how we can do this one? How we can do this one? So minus eta, I want right here. So delta Wij equal to minus eta. Dou E by dou Wij can be written as dou E by dou Oj and dou Oj by dou Wij. So that's equal to minus eta. Dou E by dou Oj is nothing but, so keep it aside. Dou Oj by dou Wij. Dou Oj, dou Wij, you have the x. So keep it x here. Now I have the dou E by dou Oj. Now dou E by dou Oj can be written as, because Oj is the function of Oj. So I want to write dou OK by dou Oj. Now what we have here? Minus eta x dou OK by dou Oj. So you have the WJK and you have the dou E by dou OK. So we know the dou E value, error value, error equal to this one. And I'm trying to differentiate this one with respect to OK. Then what happened? This two will be cancelled. This two will be cancelled. So what we have now? So what we have for this one? I think it will be 1 by n sigma k equal to 1 to n x minus OK. That's it. So finally, I can write delta Wij equal to eta into x into 1 by n into sigma k equal to 1 to n, because with respect to k, you have to increase. You have to sum it x minus OK into WJK. So this is how we can calculate the delta Wij. Now update the Wij equal to Wij plus delta Wij. So this, like this, you are going to update the weights for the decoder and also weights for the encoder until what? Until how much time we are going to update this one? Until you are getting your x value almost equal to OK. When x equal to almost equal to OK, then what happened to the delta Wij? It is almost equal to 0. Then weights will not be updated. When x equal to OK, then delta Wij equal to 0, then weights will not be updated. Then you can stop the algorithm. And similarly, here also, WJK, when x equal to OK, this difference will be equal to 0. When this difference equal to 0, delta WJK equal to 0. When delta WJK equal to 0, so there is no updates in the weights. So if there is no update in the weights, means errors are that error is almost equal to 0, then you can stop the iterative algorithm. Error equal to 0 means you are getting the output from the autoencoder almost same as your input. So this is how the algorithm will work. This is how algorithm will work in case of the autoencoder. It is almost same as your neural network. The only thing is we are trying to compress the layer. Maybe sometimes we will use the neural networks like this, but autoencoder bottleneck like this. That's it. Only that is the difference in case of the autoencoder. So, Kiran sir, is it okay? Somewhat?
Yes, sir. It's okay. I have one doubt, sir. Now we have input features. We are, yes, sir. Is my voice audible, sir?
Now I am trying to. I think you are clear with the autoencoder architecture and its mathematical background. And now I am trying to, because I am taking a very simple model, because it's easy to me to explain the flow of data and how the data will be compressed. So now I am trying to implement the autoencoder with the Python, with the MATLAB first, later with the Python.
Sir, is my voice audible, sir?
Yeah. So actually in the GitHub GitHub, I already shared the that MATLAB code also. You can simply download and open.
Hello.
So not this one. autoencoder.m. This is the autoencoder.m. Just I want to copy this complete code.
Sir, is my voice audible, sir?
So open a MATLAB, and here I'm writing the code. So what is happening? You can see. So because I'm not taking the actual data, I'm trying to explain very simple manner. Okay. So CLC, I think you are clear with the CLC. That is the clear the command window, and the clear all. Clear all means you have to clear the all the variables which are available in the workspace in the previous execution. Now this is my original data. So what is my original data? You can see my original data is, my original data contains four rows and 3 features. My original data contains 4 rows into 3 features. Now I want to convert these 3 features into a single feature. I want to convert these 3 features into a single feature. I want to compress the data from the four samples, three features to 4 samples and a single feature. Okay. Right? Done. These are my data. Now what we have to do in our autoencoder, we have to randomly initialize your weights in the encoder, and also you have to random initialize weights in the decoder. So these are the randomly I have chosen. These weights I have chosen randomly. These weights I have chosen randomly. Okay. So you can take any value. Generally, if you write the code, just only I don't have much time. That's why directly I am giving the 0.1 minus 0.1, 0.2 like that. But you can write a code also for the random weight generation. In MATLAB, by using the rand function, you can easily develop the code for the random generation of the weights also. But here I am taking some random values. Okay. So you can see this weights, how it will be. So first Wij. So Wij looks like, see, Wij 0.1, 0.01, minus 0.1, 0.2. That means, so this one, first neuron to code space 0.1, second to code space minus 0.1, third to code space 0.2. So this is what it is showing here. And similarly, Wjk. So Wjk, see, so this is only one code space, 1 to 1, 1 to 1, 3. That means 1 to 1 first neuron, 1 to second neuron, 1 to third neuron. That's why 1, 1, first row, first column, first row, second column, first row, third column. So these are the random weights I have initialized. And like I want to run this algorithm for the 100 epochs. I want to run this algorithm for the 100 epochs. Okay. So if you want to run the algorithm for the 100 epochs, now I am writing the code. So this is the outer loop for the iterations. And where inner loop, I want to pass the sample by sample. That means my batch size equal to 1. I'm passing the sample by sample. I'm taking the sample 1, sample 2, sample 3 until how many number of samples are available in my data. Okay. So after taking the sample 1, what I am doing this, that sample data, that means sample equal to 1, let us assume. So coming to the data, see, the sample equal to 1, then first sample data you have to take. This is the first sample data you have to take here and multiply with your weights. That's what I'm explaining here. Sample data multiplied with weights. The sample data multiplied with weights. Okay. Now you got the OJ. And later you want the OK. How we got the OK? OK equal to OJ multiplied by WJK. So now I got the output for the decoder or output layer at the output layer. So once you got the OJ and OK, now what we have to do? We are going to calculate the change in weights between your code and your decoder. Sorry, your code and output layer rather than the decoder. In the decoder part, I am trying to find the change in weights. How we calculate the change in weights here? So already we discussed it, right? So you can see delta Wjk, eta, that means I have taken the eta equal to 0.1. Okay, eta equal to 0.1. And x means from the data sample I am taken. From the data, the sample I have taken. Next, OK. Now this is the OK. Okay, and multiplied with OJ. Next, divided by total number of samples. So total number of samples, this is the formula, because total number of samples are total number of samples is nothing but the 3 only. You can see size of Wjk, comma 2. It will give the 3 only. So that's it. Total number of, sorry, not samples. So total number of neurons in the output layer. Total number of neurons in the output layer. That is the N. That is the N. So that's what I am writing. And once I calculate the delta WJK, now I am updating. WJK equal to WJK plus delta WJK. Okay. So the, yeah. Yes, sir. Yes, sir. Actually, we have to use the bias also, but this code will become very large. We don't have that type. But actually, in autoencoder, we have the bias also. I said in the while drawing the architecture, also I said that this is a very simple architecture and considering the only weight parameters, but actually we have the bias parameters also. So we are going to update the bias parameters also. So next, delta Wij. So we have to calculate the delta Wij. So if you want to calculate the delta Wij, so what we did here, delta Wij. So how we calculate delta Wij, you can see the formula. So delta Wij, we derived delta Wij equal to eta into this summation between x minus o into Wjk. So that the first I want to calculate the summation, and for that summation I multiplied with the learning rate. Later I divide with the number of neurons in the output layer. Then I will give the delta Wij. So you can see here. So summation, what is the summation between x minus o into Wjk? See, x means data sampling. O means OK. That means x minus OK. X minus OK multiplied by Wjk, and you have to sum it up for all the neurons. You have to sum it up for all the neurons, k equal to 1 to n in the output layer. That is the summation. Once you got the summation, then this one should be multiplied with eta. Whatever the count I have, that should be multiplied with eta. And it has something, we have the x. We have to multiply with x. X means your sample again, x. Okay, and divided by size of Wjk comma 2. That means number of neurons in the output layer. This will give the your delta Wij. Once you got the delta Wij, simply you can update the delta Wij equal to delta Wij. So this process will be repeated until maximum change in weight in the encoder, maximum change in weight in the decoder is less than some threshold value. I took the 0.001 almost equal to 0. So if the change in weight is almost equal to 0 means, the difference between these two almost equal to 0. That means x equal to OK. If x is approximately equal to OK, it's almost equal to 0. Then you got the almost equal to 0. Or you can go for this also, Wjk also. In case of the delta Wjk, if it is almost equal to 0 means this part equal to 0. When this part will be 0? When the input value and output value almost equal to 0. Almost equal. Then it will get this 0, right? So until that, this iterative algorithm will run. Okay? Hope you understand. So now this is only for the training. Now let's assume the training was completed. Weights are updated so that the difference between your output coming from the autoencoder and the decoder part is almost equal to, not exact, almost equal to your input also. Whatever the difference between the two, that is the loss of information from your data. That is the loss of information from your original data. Okay. So let's assume I am satisfied the difference between my input and predicted values in the autoencoder. Now this algorithm will train, it's coming out of it. So once it's coming out of it, now actually what is the purpose of this autoencoder?
Dimensional
to compress the data. To compress the data means from where you have to take the features, from where you have to collect the features. Compress the data means from where you have to collect the features in the autoencoder. So you have to collect the features from the code space. That means middle code space. So how we got the code space value? So if you want this code space value, what are the values available in the code space? If you want this code space value, what you can do? You have to pass the sample after training. After getting the delta Wij and Wjk. And if you want, you are collecting the reduced features or compressed features from this code. How we get the values from here? So you have to give your original samples and multiply with Wij. Then whatever the resultant is coming, that is your extracted feature. So that means you forget about the decoder now. Once the training was completed for your autoencoder, and if you want to use the autoencoder for the dimensional reduction, so you have to collect the reduced dimensions from the code space. Then you simply ignore about this part. If you ignore about this part, just give these values and multiply your weights and finally collect the features from your code space. So for that one, I am writing this part. So reduced features. So how we get the reduced features? You have to multiply your each sample with Wij. With the Wij. Then it will give the your reduced features. So now I want to run this code. Yeah, I want to save this one somewhere desktop. AE autoencoder, I will write. Change folder. So that's it. So actually, my original features are my data. Data will represent my original features. This is my original feature. And my compressed features are, so these are 4 rows and 3 features, 4 samples, 3 features are converted into 4 samples with a single feature. Now, what the loss you are getting, I think error may be available. What will be the error I am getting here? I think we have a variable called error. No, not calculated. So not calculated actually here, but you can, how many iterations it took? So iter equal to 100 iterations. It took the 100 iterations almost. And what is the maximum difference between Wij? This part I want to see. What is the maximum Wij? So maximum Wij equal to almost equal to 0. So Wij almost equal to 0 here. And what about the maximum Wjk? Maximum Wjk. So maximum Wjk equal to almost equal to 0.006. 006. Okay, that means almost equal. Wjk and Wij almost equal to 0. Not exact 0. I am saying again, not exact 0, almost equal to 0. So almost equal to 0 means your X and O values are almost equal to 0. So that's how your autoencoder generally works. So this is a small autoencoder I explained in the whiteboard, and that same autoencoder I am building using the simple MATLAB code for easy of understanding. Okay. So is it clear the operation of the autoencoder?
Sir, am I audible?
Okay. So next, I am trying to build the autoencoder with the Python. I'm trying to build the autoencoder with the Python. No, sir. Kiran sir, your voice is not audible. My voice is okay. At least if your voice is not audible, okay, you can interact with me through the chat box. If my voice is audible, that's fine now. Okay, thank you. So actually, I took very small autoencoder and explained mathematical modeling behind it. And based on the mathematical modeling, I write a small code in the MATLAB. That's the structure, that how it works actually. Can we look autoencoder as a 2 separate models? Purpose. So is there any purpose to use the decoder? You can use as a separate models, definitely. But the problem is what you will give at the code space. In case of the encoder, yes, encoder and decoder. One is the encoder, another is the decoder. Definitely, that's what I'm saying. So autoencoder has the actually 3 parts. One is the encoder and another is the decoder. In between the bottleneck part is called as the coder. You can see it as the 2 different architectures back to back connected with like a mirror image. Why we need to iterate for the encoder part? Not only encoder part, sir, we are iterating both encoder and decoder because we are giving the input and we are calculating the output of the coder, and from the output of the coder we are calculating the output of the output layer, and we are calculating the error, and we are going to back propagate the error. So you want to back propagate the error, you are back propagating the error means you have to pass the error to the decoder, and from this decoder to again encoder. So we have to do it. So we have to do the iterative part in the both decoder side and encoder side. Once the training was completed, we will use only the weights in the encoder part. We will use the weights in the encoder part because I want this output, reduced or dimensions or reduced features which are available in the code. If you want this one, you have to use only Wij, multiply the Wij with your input features, you will get the output. Thank you. Now we will discuss about the same dimensional reduction using Python, autoencoder in Python. So as usual, I will move some like forward. Okay, we have a time. Again, mount Google Drive. We have the multiple architectures, sir. We have the simple, we have the PCA, we have the factor analysis. So as of my knowledge, so if you want what will be the merit of autoencoder, whether it is performing well when compared to the PCA or not. So try to suppose if you how many principal components you want to take from the based on the principal component analysis, how you choose how many principal components you want to consider. Is there any criteria? So we have to give some parameters like variance. Then maybe based on that variance, you identified as a two principal components. Let us assume. Okay. Now the two principal components use aside to train another your machine learning model or deep learning model for your prediction. Keep it aside. Now from this your original data, now try to extract two. How many principal components you consider? You try to extract the two features at the quarter space. Now with this quarter space, try to train the same model what you are using for the forecasting. Now you can see the performance. Maybe that is one idea. Maybe based on our experience, we can get something else also. Justification. So as of now, I am observing everything and I'm comparing. So that's it. No. So we will not get same. Actually, we work with some problems and we compared also. But anyhow, we can work from your end. You will definitely observe the difference between the two, the which will perform well. Both are not same, sir. That's true. That is based on the variance and some statistical methodology. We are applying the principal components, and this autoencoder only based on the your linear algebra maths. Now pandas, and now I am loading the data. Now my data is available. So up to here, that's not a big issue. Same. So now my data, this is my data. In my data, what are the total number of input features? Forget about the don't touch your output feature. Don't touch your output variable. Dimensional reduction is mainly focusing on the input features only, not your output variable. So now how many number of input features are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now 10 features are there. Now I want to compress these 10 features into the 4 or 5 features. Let's assume I want to compress into the 4 or 5. No, I will see based on my code. Yeah, I want to compress it to 4 features. Okay. Now from this data, I don't want to touch this output variable. So then I am trying to drop that output variable. Just I'm dropping that output variable. Now my load features are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is my input features. I'm dropping the output variable. Okay. Now I'm trying to, because I'm trying to train my model, so I'm trying to normalize the data. Without normalizing also, you can proceed. It will not create any big issue. Normalizing the data. After that, you have to take the required libraries. Import the TensorFlow as a TF alias name. From the TensorFlow Keras layers, take the input layer and dense layer and import the model. So these are the, you have to remember, these libraries are required if you want to build the autoencoder. And number of input features, actually, a number of features in your original data. So number of features in the original data is equal to 10. We know already it is equal to 10. Okay. So up to here it is clear. Now come to actual. Now build the encoder part. First build the encoder part. So encoder part, how I want to build the encoder part for this problem? I want to draw now. I want to build the encoder like this. So how I want to build the encoder is 1, 2, 3, 4, 5 up to 10. And later 1, 2, 3, 4 up to 9. So this is the 10 neurons, 9 neurons, and is like that 8 and 7 and 6 and 5 and 4 again back 5 mirror image 6 7. It is very difficult to explain the mathematical analysis, back-end mathematical analysis for a very complex autoencoder model. So maybe again run that 6, 7, 8, 9, again 10 in the output layer, again 10 in the output layer. So 10 in the input layer, I want to see the same in the output also, again 10 in the output layer. Now again 10, 9, 8, 7, 5, 4, 5, 6, 7, 8, 9 back. So it is like a bottleneck. I want to build this auto encoder. I want to build this auto encoder using Python. Now see, encoder input. So what is the encoder input? What will be the input shape? That's the number of features. For our encoder input, so whatever the number of input features there, those are the 10. The 10 I have mentioned. 10 not mentioned, n features. Number of features already mentioned as the 10 here. Okay, this is completed. Now, after that, we have to add a dense layer or hidden layer with 9 neurons. So dense layer with 9 neurons. And I'm taking the activation function ReLU. You can take the linear also. Linear, whatever you want, you can take. Seek the performance of the model. That's very important. And later 8, 7, 6, 5, 4. Encoder is completed. 9 neurons, 8 neurons, 7 neurons, 6 neurons, 5 neurons, 4 neurons. So this the encoder part is completed. Okay. So see for the first hidden layer, your input is the after. Upon the input, you are adding the first layer. Upon the first layer, you are adding the second input. On the second layer, you are adding the third layer. On the third layer, you are adding the fourth layer. On the fourth layer, you are adding the fifth layer. On the fifth layer, you are adding the latest space or code space. The code space containing the 4 variables, 4 features, 4 neurons. Now, each encoder part is completed. Now, coming to the decoder. Now, decoder will start from 5, 6, 7, 8, 9. You can see. So decoder part. So decoder part, after 4, what starts? 5, 6, 7, 8, 9. At 10, you have the output. So output also a dense layer, but this output will come above your layer 5. Your layer 5, your output becomes. Upon the layer 5, you have the output. So like that, you can build the encoder part. Simple, very. So somewhere I forget to run this cell. And here. And decoder. That's it. And finally, you can build the final autoencoder. Autoencoder is a model which has the encoder input and your final output. In between, you have the autoencoder. Your input is the encoder input. Your output is the output layer, your output. And encoder input is this one. In between, all the layers will become in this model. And next, as usual, similar to the ANN, you have to compile the model. While compile the model, you have to tell which optimizer you want to use, which loss function you want to use. I want to use the mean squared error. I want to use the Adam optimizer. Now build your autoencoder. Build your autoencoder. This is my autoencoder. 9, 8, 9, 10, 9, 8, 7, 6, 5, 4, 5, 6, 7, 8, 9, 10, like that. Now, later we have to train the model. So training model is nothing but, I think yesterday also we completed. So here steps per epoch is nothing but a number of batches, like a number, not batch size, number of batches. That means 10 batches for epoch, you have to pass the 10 batches. That means batch 1, update the weights, batch 2, update the weights, batch 3, update the weights. So number of samples in every batch is depending upon the total number of training samples divided by 10. That's it. And autoencoder dot fit. So in case of the training, we have to give the input and output, right? So in case of the autoencoder, your input and output both are same. Your input and output both are same. Okay. So now run this one. So we are getting the some losses like this. So the loss is more means the deviation from your input feature and extracted output will be more. In the output layer, what are the outputs you are getting? So that is almost close to your input feature, then your loss will be almost equal to 0. If it is large means, then the deviation is more. When the deviation is more, that means most of the information. Deviation more means loss of information is more, then definitely it may have impact on your machine learning performance. Make sure that your loss will be as low as possible. Then only your extracted feature has the similar information what your original features have. So training is over. Once the training is over, what we did in case of the MATLAB, once the training was completed, we are not taking the decoder. We are using the only encoder part to calculate the reducer features. We are calculating the encoder to calculate the reducer features. So encoder, I'm taking the only encoder. Encoder contains a model. Encoder, for encoder, what is the input? Sorry. For encoder, what is the input? Your input features. So encoder, your encoder input. What about the output? For the output, what is the output? Code or latent space, this part. Code or latent space is the output for your encoder. Your encoder input is your input features. That's how I am building my encoder model. Encoder equal to, for encoder, what is the input? From where you got the input? From the encoder input. And from where you take the output? From the latent space. From the latent space. Okay. Now, for this encoder, dot predict, give your all the training samples, then you will give the your extracted or compressed features. You can see. Now, you can click here. Actually, now it says only 1, 2, 3, 4 features only it is giving. So actually, my data containing total 10 features. So from the 10 features, I am trying to compress into the 4 features. So these are the 4 features I am getting. So that's how now you can use this data for your model, which you are trying to use for the whatever the application you are working. For this data, you have to use it. Like that, you are going to compress the data, but you have to justify later. So whatever the change in the loss or change in the accuracy with the original data and with compressed data, whether the deviation is more or if the deviation is less, deviation is reasonable, and how much model reduction is there, how much complexity the model is reduced, everything you have to analyze. So if time permits, I will show one paper. I think. Okay, I will show later if anyone wants. So I will share in the group if required that paper. So we work on some dimensional reduction technique based and we compared. We were going for the dimensional reduction technique to say that to build a compressed model or lightweight model. When we build the lightweight model, what about the accuracy or loss? So we have to justify both parameters. We have to justify both ways. So I will share the paper with if required later. So this is about the implementation of the auto encoder. Okay, using Python, using MATLAB, I have explained now. Now I want to explain about the implementation of the neural network using the MATLAB. So implementation of neural network using the MATLAB. Okay. So first I want to see whether the data is available or not. Downloads, data. Yes, I think load is the data. Yes, I have the data, right. Now I want to okay. So take the path, copy path. So I want to take the data equal to, I think use XLS read and pass my path where the data is available. So in that path, that data is available. I want to build the neural network ANN model using MATLAB. Now it is taking that, yeah. So this is my complete data. This is my complete data, which is available in that Excel file and assigned to a variable called data. Okay. So now my data variable, 1 minute, 1 minute, please. I want to clear my complete workspace. Now I want to run the same data loading code. Now you can see that variable, data variable here. So this is my data variable. The data variable contains the complete data set. This is my complete data set. Have the 10 input features and the last one is my output feature. 10 input features and the last one is called as the output feature. Okay. Next. Now what we have to do? We have to split the data. What are the inputs and what are the outputs? We have to split the data. What are the inputs and what are the outputs? That represent inputs with X. So X equal to in the data variable. So all rows, but how many columns? First column to 10th column. These are called as my input features. I think you agree. In my complete data, so in my complete data, I have the 11 columns. Out of 11 columns, the first 10 columns are my input features and the last column is called as the output variable, right? So first 1 to 10 features are the input and y equal to data of colon, comma, 10, 10th column, not 10th column, 11th column. In my 11th column, so whatever the 11th column is there, that is my predicted variable, the output variable. That's it. Completed. I have separating the input features. It is a 23,304 10 features inputs and y equal to 23.304 cross 1. That means only one output variable. Later, you have to type NF tool. Type NF tool on the command window. Currently, I am using the MATLAB 2023 version. It will be different from the 2020 previous versions. It will be slightly different. So what is I'm demonstrating here, maybe same thing not visible for you in other older versions, but you can do with the older versions also. I'm trying to explain. I'm trying to explain with the toolbox. Okay. Now, in the toolbox, by default, they give the 2-layer feed-forward neural network with sigmoid activation function and linear activation function in the output layer. Okay. So 2-layer, in the hidden layer, you have the sigmoid activation function, and the output layer, you have the linear activation function. You have the weights and also you have the bias parameters. You have the weights and you have the bias parameters and you have the sigmoid activation function here and you have the linear activation function here. So this model, it will build. Okay. Now import. Click on import because we have to import the data. So predictor, that means input. What are the input now? Where the input are available? In X. Responses means output. Where the outputs are available? Y. Inputs are available where and where the outputs are available? X and Y. Okay. So row wise same. Actually, in both cases, you can see. In both cases, rows are same. X input side 23,304 rows. Y also 23,304 rows. Both are rows are same. So as the rows are same, here you have to enable the rows. Just click OK. Just click OK. That means data loaded. Once the data loaded, you have to split the data. What percentage you want to give? I want to use the 70% for the training and 15% for the validation and 15% for the testing. So you can change, you can play with these values. You can play with these values. Accordingly, your training data also changes. Suppose if you keep here 25, and if you keep here 25, then it will become 50. So that's your choice. Huh? So here I'm using the 15% for validation and 15% for the testing and 70% for the training. Okay, this can be it is in your control. And another thing in your control is how many number of neurons you want to keep in the hidden layer. How many number of neurons you want to keep in the hidden layer, that also in your control. Let's assume because my number of input features equal to 10, based on our 1.5 concept, I want to keep the 15 neurons in the hidden layer. I want to keep the 15 neurons in the hidden layer. Now, simply click on the train button. So training is started. It is around 1000 epochs. So but it's not running up to 1000 epochs. It stops by 28 because actually in the MATLAB toolbox, the stopping criteria is based on the two things. One is the maximum number of iterations and also based on the number of validation checks. So validation checks means if the validation error is continuously increasing for the 6 iterations, then it will be stops. If the validation error is continuously increasing for the 6 iterations, then it will stop. Okay. So it will stop here. So if you are not happy, now finally you can see what is the error, mean square error you are getting. So mean square error should be as low as possible and your regression value R should be more close to 1. If model is performing well means your regression coefficient R should be more close to 1 and your mean square error will be as low as possible. Don't think that, sir, you are getting the 10 to the power 5 like that because my data has very large values. I'm not using the normalized data. If you use the normalized data, then you are able to see the very small values. But here I'm saying that I'm able to see 10 to the power 5 like that because my data has contained a very larger value. That's why it is able to see like that. But make sure that the difference is as small as possible in comparison with your data set. Suppose if the performance of the model is perfect, let us assume. If not, you can tune your number of neurons in your hidden layer and retrain it. And you have to retrain it until you satisfied. Okay. So, and you can see if you click on the performance, so you can see the performance plots. You can see the performance plot. So how this performance plot is varying. And also you can see the error histogram. If you want to see the error histogram, click on this error histogram. Error histogram means every error coming how many times during the training, during the validation, and during the testing. How many number of times that error is coming, that will be shown in the error histogram. Okay. And so these all are the some analysis part only. From the analysis part only. Now let's assume you, a supervisor, a client, whatever it may be, you are happy with these errors, with this regression coefficient. Now you want to deploy the model. You want to deploy the model. So if you want to deploy the model, what you have to do is just click on this export model. You can see export Simulink. Click on export Simulink. Now trained model, let's assume you are happy with the performance of the trained model. Now this trained model I want to deploy. So export the whole model as a block, a whole trained model as a block. So inside your trained model, you have the weights and bias parameters, but that is not visible. It's like a black box now. When you are using the toolbox means it's like a black box. You don't know what happened inside. But you have some idea how neural network works. You can get some clear picture. What will be inside your ANN toolbox now? ANN box now. Trained ANN box now. And after that, yeah. So this is my neural network model or ANN model, trained neural network model. If you click here, nothing will be visible to you. That's it. You don't know anything what happened. But inside you have the weights. Okay. Now, once the trained model is readily available, then what will you? If you give some input, it will be able to give the some prediction. If you use some inputs, it is able to give the some prediction. So let us assume, click on the library browser and go to Simulink, go to Sinks and take the display block. And delete here and connect this display block to your model. That's it. Okay. Now click on the input and actually you are expecting the inputs 10 inputs, right? So I want to give the 10 inputs randomly, just only prediction only. Just I am taking 1000, sorry, 1000 semicolon, 1100, sorry, 1100 semicolon, 1200 semicolon, some 1100 semicolon, price let us assume 10,000 semicolon, and 11,000 semicolon, 12,000 semicolon, like that you can 14,000 semicolon. So 8, and day status, let us assume 0. That means 0 means weekday. And season, let us assume summer. Summer means rainy summer and winter. So that means 1. So just you give, if you apply, okay. Now run this model. Now run this model. For small 1 second, you can run and run this one. So it is predicting my load based on my given input features. Now my neural network predicting the load of 1036. So like that, you can deploy the trained model using the Simulink in the MATLAB. So I think you are clear with how we split the data in the MATLAB, and how we train the data using the MATLAB toolbox, and how we deploy the your ANN model. All we discussed now. But on the limitation here is, what the limitation here is, you have a control only on the number of neurons in the hidden layer. If you want to use the toolbox, you have a control on the number of neurons in the hidden layer. You can't change the number of hidden layers. You can't change the activation functions, right? And you can't change the optimizer. Which optimizer you want to use, that also you can't change now. So here, which algorithm it is using? Levenberg-Margaret algorithm. By default, it is taking that one, right? And it take the 15 neurons, it is in our control, but number of layers, it contains only one hidden layer. You can't use the 2 layers or 3 layers. That is not in your control. And in this toolbox, in sigmoid, you have in the hidden layer, you have the sigmoid activation function. In the output layer, you have the linear activation function. You don't have any control to change that one. So that is the limitation of the toolbox. So that's why I'm trying to explain, instead of going with the toolbox, I'm trying to explain the code, how we can build the neural network model using the MATLAB. How we build the neural network model using the MATLAB, that we are going to, I'm trying to explain. So this is my code. I already, this code also shared in the GitHub, so you can go through it. Okay. Now I'm trying to explain the code. So as usual, CLC clear all to clear your command window and to clear the workspace. Later, from my download folder, I have the load file, Excel file, and I am passing the data to my variable called load. So I'm reading the data available in the Excel sheet in the download folder, assigned to a variable called load. Okay. So after that, what I'm doing here is I'm trying to do the data normalization. So data normalization is done like this. How? Normalized data is equal to our original data minus minimum value divided by maximum value minus minimum value. We know, yesterday we discussed it. So this is the data normalization part. Once the data normalization is completed, I want to split the data like inputs and outputs. What are the inputs and what are the outputs? But as I said, that splitting of the data can be done randomly. So for that reason, here what I'm doing is, these 3 lines of code is used to shuffle the samples. I have the 1000 samples and I want to shuffle the samples. After shuffling the samples, I am splitting the data. Few are for the inputs and few are for the outputs. I hope you are clear. So what I'm trying to do here is, I have the X1 to X10 input features. I have the Y1 output feature. I have the 1, 2, 3, 4, 5, 6, 7, 8, 9, like that, thousands of samples. Now I am shuffling the data. This row here, this row here, this row here, this row here. I'm shuffling the rows because you have to pick the randomly, right? Not in the sequence manner. You want to pick randomly. So to pick that randomly, what I did is I shuffled the data. After shuffling the data, I took the some 80% of data for the training and remaining 20% of the data for the testing. Like that, I am splitting the data randomly based on the shuffling concept in the MATLAB. So that's what I am doing. After shuffling the complete data, now first 10 columns are the inputs, and the last column is called as your target. First 10 columns are the inputs, and last column is called as the target. Okay, that means X and Y I am divided. X and Y I am divided. So that's why this is called as the data normalization, and this is called as your data division. Input, what are the inputs and what are the output? What are the input and what is the output? Now, coming to the model building. Now we will discuss about the model building. So you can write train FCN. This is a variable. You can use any variable, train FCN. That means which algorithm you want to use. If you want to use the Levenberg-Margaret algorithm, you can use train LM. If you want to use the scaled conjugate gradient, you have to use train SCG. If you want to use the Bayesian regularization method, you have to use the train BR. Okay. Now I am to use the train LM. That means Levenberg-Margaret algorithm. So that you have to assign which algorithm you want to use. Next. What is the architecture? What is the architecture of your neural network? This is the net is your object of your ANN model. It is a FitNet or ANN, FitNet, fit network, feed forward neural network, ANN model. Here within the bracket, I am using the 45, 45, 45. That means my ANN model has a 3 hidden layers, and every hidden layer has a 45, 45, and 45 neurons. Every hidden layer has a 45, 45, and 45 neurons. And for this network, I am passing the algorithm. Which algorithm I am passing? Train LM. Train FCN equal train LM. That algorithm I am passing. Now you have a control, right? So if you want only 2, then you have to remove this one. If you want 4 hidden layers, you can add 1 more. And if you want to use the 4th layer, if you want to keep the 50 neurons, you have to keep 50. Like that, everything in your control. So number of neurons in your control, and number of layers also in your control, and which algorithm you want to use, that also in your control. And not only that, what else? You have 3 layers, right? Layer 1, layer 2, layer 3. For the layer 1, which transfer function you want to use? Sigmoid. Tan sig means sigmoid. Tan sig means tan hyperbolic function. Log sig means sigmoid activation function. ReLU. So which you want, you can use that one. I want to use the tan hyperbolic function. So tan hyperbolic function for the layer 1, tan hyperbolic function for the layer 2, and tan hyperbolic function for the layer 3. But in case of the toolbox, that control is not there. By default, we have to use the sigmoid activation function. And in the last layer, output layer, I want to use the linear activation function, or if you want to use the sigmoid, you can use the log sigmoid also, because you have the normalized data. That's how you can build the neural network. Next, data division. So here, data division, nothing but the input and output, the X and Y. But here the division is for the training, validation, and testing. This is the block for the random splitting of the training data, validation data, and test data. Training data, validation data, and test data. Okay. So training is 70%. You can change 70, 15, 15. You can keep 80, 10, 10. That's your choice. 90, 5, 5. You can have a control that one. Data splitting also. Only you have to change these 3. 70, 15, 15, 80, 10, 10, or 90, 5, 5. That's your choice. After that, you have to give the learning rate. Net dot train param dot LR means learning rate. So I want to give the learning rate eta equal to 0.05. And I want to run the model for the 5 epochs, because we don't have much time. So 5 epochs. And which metrics you want to use to analyze the performance of the model, to update the model parameter. That is called MSE, mean square error. Okay. Now model is ready, data is ready. Now you want to train the model. If you want to train the neural network model, so you have to pass, train, pass your network, and pass your inputs, and also pass your targets. So pass your inputs. What are the inputs already available? This is the input features, and target, output feature. Pass your input features, output features to the net. Net is already defined here. Net is already defined. Your neural network is already defined. For that neural network, pass the input features, target variables, and train it. Once the training is completed, so let's assume the errors are good, then what you can do? Once the training is completed, then it is called testing. That means testing prediction. So if you want to go for the prediction, for the trained neural network model, pass the inputs. By passing the inputs, calculate the output. And what is the error? So error is nothing but the difference between your target value and your output value. So this is how we can build the ANN model using the MATLAB. Okay. Suppose if you want to execute this complete code, So this code is already available in the GitHub, which I have shared with you. Now I want to run this complete code. It is a busy means it is a training. So, so it will train, okay, no problem. It will take some time. So I'm trying to conclude this session for this complete FDP. So in this FDP, we discussed about the data analysis. We discussed about the artificial neural network and its implementation using the Python and MATLAB. And already Sir explained about the convolutional neural network and recurrence neural network. But actually, we don't have much time. That's why we are unable to adjust that time. So image classification using CNN, I have to tell, but already that code is posted in the GitHub. So go through it. If you have any issues, please send a message. We will discuss, no problem. And RNN also already build the code using RNN for the load forecasting. That also, there slightly few more code is added, need to be added. Training was completed, testing was completed. Now I want to deploy the model. So still it is not completed. I will already without deployment part, remaining code is already uploaded in the GitHub, and soon I will add that deployment code also. So you can go through that code also. If you have any issues, you can revert back. We will discuss. If you have any issues, we will discuss on that. But it will take more time because of my system configuration and because of the data. So I took only 5 epochs. Don't expect the better performance, but only to say the steps, to demonstrate the steps how we can build the ANN model based on the code, not based on the toolbox in the MATLAB. But still, this code also will not give the clear idea about what happened behind, because still we are using the functions in the form of the code. If you write your own code from the scratch based on the backpropagation algorithm, then you will get some clear idea, but only that one for understanding the backpropagation algorithm. But if you want implementation, don't go for write the code from the scratch. You can use the toolbox, you can use the MATLAB code, or you can use the any Python libraries. Okay. So once again, thank you all. Any comment or any feedback from actually the 11 part? So I want to any feedback from your end, any comment. And meanwhile, actually I posted only one assignment in the Canvas. So soon, within a couple of days, within 1 or 2 days, I will post the few more assignments in the Canvas. So try to complete by Monday. Okay. And meanwhile, I will prepare the participation certificate and I will share those participation certificate to your registration mail ID. So please, any comment from your side, if anyone is there? Any feedback or comments from your side on the FDP? And one more small request, I will share one feedback link in the WhatsApp, to the WhatsApp. So please respond your valuable feedback that will help us to improve for a betterment.
Venkatramana.
Madam.
Good evening, ma.
Good evening, madam. Thank you, madam,
thank
for
you.
joining.
Really, they were very interesting, and you could share your practical experience, whichever you have achieved while pursuing your PhD. Really, like any subject, no, unless we do practical, like lab oriented, we cannot get the complete clarity about the subject.
Right, madam.
So
right.
really, I have learned in 2001 and applied for my PhD, but advanced topics like recurrent networks I did not do. So really interesting. Even whatever you were explaining about your problems also, it was very interesting. Thank you.
Thank you, madam. Thank you very much, madam.
It is really like schedule is very good. Like because morning times I had classes, afternoon I was free, so I could accommodate all the 5 days.
Okay,
so thanks a lot. So in future also any advanced topic if you are planning, I personally will join.
Thank you, madam. Thank you very much, madam.
Welcome, welcome.
Anything from others?
Good evening, sir. This
Sir,
is Satyanarayana from full-time research scholar, sir.
sir.
This 5 days faculty development program is very much useful to scholars and MTech students, also BTech students, sir. Really, we got much knowledge regarding all the ANN networks, fundamentals of artificial intelligence network, and basics of writing the codes for developing the codes for the whatever practical done. Sir, it is very useful for us, sir. Thank you very much.
Thank
for
you,
this
sir.
opportunity, sir. Thank you
So
very much.
actually, sir, if any participants are there in this meeting, so my suggestion is, if we attend any FDPR workshop, if you later we have to apply for even a small problem statement for a small project, then only we are able to get the complete scenario. Then only you are able to understand. Then only you are able to remember for a long time. Otherwise, it is very difficult. Okay. So my personal opinion and personal suggestion is not only this one, which workshop you are participating in future. So at least you gain a small percentage. With that small knowledge, try to work on related to your domain. Definitely that will help you to understand the concept what you learned in the FDPR workshop, and that you are able to remember for a long time. Otherwise, after 1 week or 2 weeks, you forget everything. Well, again, you have to start from the zero. So that's my suggestion for all the participants. Okay. So once again, thank you all of you for your for your interaction for the last 5 days. So because if no one is interacted in the online session, so then the instructors may feel some bored because whether they are listening or not. So thank you to all the participants who are interactively participated in the last 5 days. Still anything anyone wants to speak something? Unmute yourself, you can speak. Otherwise, we can end up this FDP for today. And within couple of days, I will share the participation certificate. And within couple of days, I will post some assignments in the Canvas. Try to attempt them to understand, to know ourselves how much you gained. That will give some boost for us. Based on your performance, that will give boost for us. That is only the reason we are posting some assignments in the Canvas.
Sir, hello.
Sir.
Am I audible, sir?
Yes, sir. Yes, sir.
Yes, sir. Actually, I was working on deep learning models before too,
Sir.
but the mathematical intuition was missing actually. So Vinod Kumar sir's class and your explanation of the basic code, that was really helpful, sir. So I hope there will be much more sessions on this, and I would request you to add lab assignments every day in your future FDPs.
Right.
That would be very helpful actually.
Right, sir. Right.
Thank you very much, sir. Thank you.
Thank you, sir. Thank you very much, sir. Okay. Thank you very much, sir. I'm trying to end this FDP for today. Thank you. And I will post one feedback link in the WhatsApp. You can provide your valuable feedback. What you feel, you can write, no problem. So to make, to understand, to analyze, for our betterment. So that's it. Thank you once again to all of you.